we're going to be looking at some GCSE papers. So, if you don't know how the British school system works, essentially, when you're 16 years old, you have to take something called GCSEs. They used to be called O-levels, but essentially these are kind of standardised exams that all children have to take. And so this is essentially the bare minimum level of knowledge that any adult is expected to have in a topic. So the average person gets a B or a C. That's like the average grade, right? But anyway. So it's I think it'd be quite good. Whereas I am an actual physicist, that's my job. So I figure we should be able to do these quite easily. But it'd be interesting to see what, it's very easy when you're an expert, when you're very advanced in a subject to forget where that baseline is, for everyone is. Like there's a brilliant KTD comic about some chemistry majors or something. They're talking about, oh well, obviously everyone knows at least the makeup of quartz, right? It's like, in terms of its chemical components, it's like obviously not, right? But that's the point. And it's very easy to do that. So this is kind of an effort, I suppose, for me, so that I know if I'm talking to a layperson, I know exactly, or someone not as well versed in physics as me, not like, I don't mean that in a derogatory way. It's good for me to see, right, what level do I need to go down to? Because obviously you don't want to go down too low to where they're just like, right, don't patronise me. Like, I know what I'm talking about, but anyway. So, we've got our speedrun timer here with all 4 papers. Normally you would either do foundation or higher. But as you're given, as you can see here, an hour 45, and it's an hour 45 for each paper. I kind of wanted to show that, but oh well. Okay, well, it's an hour 45 per paper, so if we hit an hour 45, I'll split and stop, but we should be able to get through a paper within an hour 45. That is meant to allow time for the student to go back and check their answers, etc. So we won't be doing that, we're just going to go straight into it. So, with that being done, I've got some nice background music. Hopefully I'm not too loud. I feel like I'm a bit too loud. I'm just going to bring me down a little bit. So that should be a bit more hopefully I shouldn't hit that. Okay, if I speak too loudly, don't speak too loudly. Right. Whatever. Okay, so here we are. I've got a whiteboard here so I can draw things, but there is text, so you don't have to watch me like struggle to write hello, right? Like that's just monstrous. I don't want to be doing that. Luckily we've got text because some of them are free text answers. So let's get started. So GCSE Physics Foundation Tier Paper 1. So Foundation Tier, what am I expecting? That's a good question. I'm expecting some mechanics. There'll be some basic electronics, so using battery, making sure you probably like Ohm's law and things about having things in series or things in parallel and how the current changes over that. We do also have the insert, so this tells me some idea of what we're going to see. Yes, we're going to see some mechanics. We've got kinetic energy, we've got elastic, we've got gravitational, so presumably talking about pendulums and springs. Changing the thermal energy, okay, sure. So maybe like radiators, because there was conduction, convection, radiation, that sort of thing. Got power as energy over time, power as work done over time. Yeah, got efficiency, yes, because there was a whole thing about I think it was GCSE where they were talking about how certain energy generation methods work, right? Like hydroelectric power and stuff like that. Here's the electric stuff. Got charge flow, potential difference, power in terms of electronic things, density, okay, sure, and lots of other stuff. And then there are some things that are only in the higher one, right? So pressure due to liquid is only higher levels. And then similarly, momentum is only at high levels, just mass velocity. Alright. But that might be why, because it talks about force in terms of momentum, and then some stuff about conductors and some waves and stuff. Cool. Alright. Well, we've got 11 questions, an hour 45. Time currently is 2:04. course paper, you must have a ruler, a scientific calculator, physics equation sheet. Okay, we do need, I will just be using the basic calculator then. I don't need a proper one. We'll have that in small thing for now. Minimized for now. That's the word I was meant to use. And then let me just mark where to try to not use that area. I shouldn't really be using that area anyway, but helps to have that in mind, so that if I do need to use it, I don't. Use black ink or black ballpoint pen. All right, we're on black. Good. Pencil should be used for drawing. Fill in the boxes at the top of the page. Answer all questions in the spaces provided. Well, we've got. I'm not going to directly edit a PDF. That's just asking for trouble. Do not write outside the box or on each page or on blank pages. Do all rough work in this book. Cross through any work you don't want to be marked. If you need extra space, use line pages. Obviously, we can just add more whiteboards, so no issues there. The maximum mark is 100. We're going to try and get 100 in all 4 of these papers. I say that should be fine, but I'm a little worried there might be some things that I've forgotten, which I may need to try and recollect. Certainly some questions can be like, explain blank, 6 marks. It's like, oh, okay, I need 6 points then. The marks shown in brackets are expected to use a calculator where appropriate. You're reminded of the need for good English and clear presentation. Right. Okay, so before we turn over the page, we'll begin the timer. Your time starts now. Right. Question number 1. Figure 1 shows a boy bouncing on trampoline. Ooh, what fun. Ooh, look at all those springs as well. Amazing. So, 1.1. What have we got? The boy falls from position in figure 1 towards the trampoline. Yes, that's what falls means. If you fell upwards, I would be concerned. Complete sentences. Choose answers from the box. Okay, so we've got some terms here: chemical, kinetic, elastic potential, nuclear, and gravitational potential. So different kinds of energy. All of that is. As the boy falls, there's a decrease in his blank energy. Okay, well, as the boy falls, his height is decreasing, right? And if we check our equation sheet, we see the only thing that's concerned with height, very commonly used as h, is gravitational potential energy. And gravitational potential energy has height in its term. So if height goes down, and everything else is the same, like the boy's mass isn't changing, and gravitational field strength is constant when you're this close to the surface anyway. It does go down as you go into space, but that doesn't matter. It doesn't matter here. So as the height is decreasing, our gravitational potential energy is decreasing. So that is the correct term. So gravitational potential. I'm just going to put GP as the first bit. And then as the boy falls, there's an increase in his blank energy. Well, it's obviously not going to be gravitational potential because we just said it decreases. I would be worried if it was nuclear. I think we can safely assume the boy does not have a load of uranium in his pockets, or is indeed made of uranium. So it does say specifically his as well. So there's elastic potential, and they put springs there. So you go, oh, springs, maybe it's elastic potential, but that would only be if it was talking about the trampoline. It is instead only talking about the boy. So the boy doesn't have any elastic potential energy. In this case, everyone should know that if you drop something, its speed increases, right? Because it falls down, its speed goes up. So anything related to speed, yes. Kinetic energy goes to speed squared, but that doesn't matter, right? The boy's mass is the same, but the speed increases. If the speed goes up, the kinetic energy must go up. So in this case, it is kinetic. Right, I will. It's just one word, so I can't be bothered using the one. So apologies for that. Cool. That's 1.1. 1.2. Now, they tell you there's 11 questions, and they split them up like this. So, right. 1.2. As the boy lands on the trampoline, each spring stretches 0.015 meters. So that's 1.5 centimeters to you and me. But here, the spring constant. It should be the spring constant, right? Of each spring is 120,000 newtons per meter. Calculate the energy stored by each spring. And it even gives you the equation, so it doesn't even tell you to use the equation sheet where elastic potential energy is there. They actually recreate the thing for you, which is a bit strange. But okay. You are meant to use this insert, right? Yeah. You must have a physics equation sheet. Okay. Sure. It's just a bit strange. I guess it's just to make sure that you really know which equation to use. This is literally just checking, can you use a calculator, basically. So, EPE, elastic potential energy. Oh, God's sakes. Oh, well, that went well. EPE, that is a half. We could write 0.5, but a half is perfectly fine too. Let's curve that. There we go. Times the spring constant. Now, the spring constant of each spring is 120,000. 120,000. There we go. I should have used text for this, but oh well. Times by the extension squared. So the important thing here is to just make sure that you write 0.015 and you put the squared there, and you don't square anything else. So there will be a mark, presumably, just for writing out like that. And this is how you show your work, is you just take the equation and you replace all the words with numbers, right? Very easy to do. It tells you the spring constant is 120,000. So you see the word spring constant, you write 120,000. Tells you that each spring stretches, right? That's just saying the extension is 0.015. So you wait to see its extension, you put 0.015, right? Now, that I can't do off the top of my head, so we'll just do that. I also have done a rather horrible thing, which is I haven't put in units, and I'm saying that equals an energy. So, yeah. At university, you might lose a mark for that, but not during school. So, 0.5. So, oh well, in my head, I know that's 60,000, right? But let's do 0.015. There is a squared. There it is. Times by 60,000, and we get 13.5 joules. Okay, and I'm happy with that answer. Don't see how that could be anything else. Tells you the equation to use, it gives you the numbers to put in the equation. It's just a matter of putting all that together. Cool, let's use a new board. 1.3. There are 40 springs on the trampoline. Calculate the total energy stored by the 40 springs when each spring is stretched by 0.015. Okay, well, 1 mark. So this is just, do you know that you just have to add all these energies together, right? So there are 40 springs, so we do 40 times our answer before, which is 13.5 joules, right? Yep, 13.5 joules. And that is 135 times 4, 540 joules. Okay. Yeah, I mean, just 1 mark. That's all it's looking for. It's just, are you doing the previous number times 40? So even if you get that number wrong, as long as you multiply by 40 in this one, you'll still get 4 marks, I'm sure. I'm pretty sure that's how it works, but we'll find out when we get to the mark scheme. 1.4. The kinetic energy of the boy as he lands on the trampoline is 600. Okay. The maximum kinetic energy of the boy after he bounces is 45% of his kinetic energy as he lands. Calculate the maximum kinetic energy of the boy after he bounces. Right. Okay. So this is asking you, do you know how percentages work? Essentially, a lot of physics, well, certainly a lot of the physics at the start is basically maths rather than physics. But there we go. So kinetic energy boy is 600. The maximum kinetic energy after he bounces is 45% of his kinetic energy as he lands, right? So all this is saying is you need to find 45% of 600 joules. And how do you do that? It's very simple. You take the number 600 and you multiply it by 45 divided by 100. Okay? Because what percent means is for every 100, right? That's why percentage can't go over 100 typically, is because you're saying for every 100 that you start with, you then have 45 of that, right? That's what percent means, per 100. So that you could actually simplify that as 6 times 45, because you move that divide over there. But anyway, I digress. So this is essentially 6 times 45, which is 90 times 3, which is 270 joules. And I keep right-clicking by accident. I apologise for that. So that's the maximum kinetic energy. So what it's looking for here, there's 1 mark for writing that, presumably, and then 1 mark for the correct answer. I would guess. I'm going through boards like nothing else. It's a good thing they are infinite. So 1.5. Why is the kinetic energy of the boy after he bounces less than the kinetic energy as he lands? And you tick 1 box. The answers are: energy is not conserved, which is a very broad statement to make. Energy is transferred to the surroundings, and the springs transfer energy to the boy. Right. So, energy is not conserved is, I guess that's only there as a check to make sure if you know that there's the rule that energy should always be conserved. Energy cannot be created or destroyed. It only is transformed from one form to another, unless you're talking about other stuff. But it's talking about very advanced physics, in which case that's not always true. But at GCSE, yes, energy is always conserved. So we know it's not the first box. The springs transfer energy to the boy. Well, that would imply that the boy gains more energy, right? If the springs are giving energy to the boy, then the boy's energy should be going up. But this is saying that it's less. So it can't be that. So it's got to be energy transferred to the surroundings. So, God, I don't know. I guess I'll just do it like this. There we go. Because I'm not writing all that out. I ain't writing all that. So this is why his energy is less, is because his kinetic energy is going down, because his energy is transferring into heat and sound and elastic energy, and all these other forms of energy that he's not then getting back straight away. So that's why his kinetic energy goes down. That's why if you bounce on a trampoline on Earth, you will stop at some point without adding more energy. 2.1. Okay, that's one question. It took us 11 minutes. Right, I'm a bit worried. we'll see how we do. A girl ran to the top of some stairs. Figure 2 shows the stairs. Wow. The girl measured the height of the stairs. What measuring instrument should she have used? A girl measured the height of the stairs. I suppose this would just be anything that can measure distance, right? I don't see why you couldn't. So, you could say, I will actually use text for this because let's say, well, I mean, if I just had to say one, I would just say a ruler. I mean, that seems simple enough. But I suppose you could also use a tape measure. I mean, I wouldn't necessarily see a tape measure in a lab, but I feel like that would be a bit better than a normal. Like most rulers, quite small. But I mean, if you had a big enough ruler, I don't see why not. So, well, yeah. Out of those, I'll say ruler, but I think realistically, you would probably just use a tape measure. So we'll say ruler for that one. 2.2. I mean, presumably though, any measuring instrument that can measure height, they can measure any distance longer than a meter or so, or at least a few centimeters should be fine. Like, obviously you don't want to use something you can only measure something like that, but like a ruler, that should be fine. The height of the stairs was 1.7. The mass of the girl was 50 kilos. I mean, yes, she ran to the top of some stairs. Fine. Gravitational field strength is 9.8 newtons per kilo. calculate the change in gravitational potential energy of the girl, and it even gives you the equation again. Right. So again, this is just like in the earlier question. We're trying to find the change in gravitational potential energy. I suppose that's a bit tricky. It says change in gravitational potential energy, but then it says just gravitational potential energy. So there may be an idea of, well, what was it at 0? But the point is, if you put in a height of 0, this number will then come out to 0, because 0 times anything is 0. So yeah, technically. So yeah, that the height kind of bakes change in, because you're talking about the change in distance when you say height. So in this case, GPE equals the mass, which is 50 kilos. We'll just use the numbers here. Gravitational field strength, which is 9.8. And the height, which was measured as 1.7. Okay, so again, it's 2 marks. There'll be 1 mark for showing your working, which is just putting all the numbers in, not just going straight from the words to the final number. And then we'll times it by 9.8. So I will bring out my calculator here. Go 50 times 9.8 times 1.7. And we get 833 joules. Yeah. So the always thing we have to check, are we using the correct units? Which is why it's good to write the units in, really. But here we have kilos, and we have meters, and we have newtons per kilo, and these are all standard units. It's fine. If this was centimeters, we would have to change it, but as it is, that's completely fine. 2.3. A boy ran up the same stairs and did 1,800 joules of work. The time it took the boy to run up the stairs was 1.44 seconds. Calculate the power of the boy. Okay, again, very simple. Again, we just say the power, which is what we're trying to do, is the work done, which we know is 1,800 joules. And we divide that by the time, which is 1.44. So this is showing the work. That's the mark there. And then that equals 1,800 divided by 1.44, 1,250 watts. Yep. I mean, not much to explain there. Again, it's just joules and seconds. A watt is a joule per second, so all the units work out fine. Don't need to... It's definitely not 1.25 watts, for example, or 1.25 million watts. It is 1,250 watts. So we know that's fine. 2.4. Which stopcock was used to measure the time the boy took to run up the stairs? Okay, so we've got A, B, and C here, so I'll just draw the 3 boxes. So, stopcock A has a 0 on it. Stopcock C also has a 0 on it. But stopcock B isn't at 0. I suppose. Oh no, I see what it's doing. Right, no. I was wondering about that. Right. So what it's doing here is testing precision. My bad. I thought it was testing can you actually read these measuring devices. It can't. It isn't. So because this says 1.44, we need to see which stopcock is precise enough to give that answer. So stopcock A, that can never say 1.44. That would either say 1.4 or 1.5. Right? So it can't be that one. We know it can't be A. I'm just going to scribble that out. Why not? Stopcock B, you could only say to the nearest second, really. I mean, maybe the nearest half a second, but, you know, if it stopped between 6 and 7, you can't say if it's, you know, you can't say if it's 6.4 or 6.5, they would look very similar. So it can't be stopcock B. So it has to be stopcock C, and that works because that could say 1.44 because it has all the space to say 1.44. So that's good. 2.5. Generally, these earlier questions have a lot more parts than later ones, so I'm less worried that we'll get to the end in time. The boy had a speed of 2 meters per second at the top of the stairs. The mass of the boy was 70 kilos. Calculate the kinetic energy of the boy at the top of the stairs. Okay. Again, just as before, we've got kinetic energy equals a half times by the mass, which is 70 kilos, times by the speed, which is 2.0, and we square that. Okay, now when you do this with a calculator, just make sure that when you're squaring, you only square the speed in this case. Just make sure that when you're calculating, what I find easiest is with a calculator, it's not always the best to do left to right. Generally, you should do the most complicated thing first, right? So because this is almost like a calculation by itself, I would type in 2 squared first, and then multiplied by 70, then multiplied by a half, right? Because these are just numbers, but this isn't a number yet. This is still something else. To show what I mean, I would type this in as 2 squared, and then times that by 70, and then divide it by 2, right? I mean, times by half, divide by 2, whatever. And we get 140 joules. Okay. So that's fine. Again, this will be one mark, and this will be the other mark. Making sure that you actually type it into the calculator correctly. Cool. Question 3, or 3.1. Figure 3 shows a plastic rod being rubbed with a cloth. The plastic rod becomes negatively charged. Yeah, you can see with all the negative charges on it. Complete the sentences. Choose answers from a box. Each answer may be used once, more than once, or not at all. Okay, so this throws a curveball. We don't know that if we pick one, the other one isn't going to be used for the other question, the other sentence as well. The plastic rod becomes charged because it gains something. Okay, so the question is, the first question really is, of these particles, which one is negatively charged, right? Because the plastic rod becomes negatively charged, so it gains negative charge or it loses positive charge. And this is saying it's charged because it gains, so it must be gaining a negative charge, which is electrons, which we write as E- when you're higher up, so that's electron. The cloth also becomes charged. Okay, so if that becomes negatively charged, so both of these were neutral at the start, right? That's obvious. Generally, most things you see around you are not charged in some way, because if they were, then something would, then particles would be attracted to it and it wouldn't be uncharged for very long. So both of these were neutral. The plastic rod became negatively charged, so if the overall charge has to remain the same, then it must be becoming positively charged. Another way of saying this, another way of thinking about this rather, is that the plastic rod gained electrons. Where did those electrons come from? They didn't just come out of the sky. They came from the cloth. So we know because the plastic rod gained electrons, the cloth must have lost the electrons. So it is, again, electrons, which I've drawn horribly there, but hopefully you can see that just fine. 3.2. What charge is left on the cloth? Okay, I kind of already answered this in my earlier, but there we go. So it's either negative, neutral, or positive charge. Well, if it loses negative, that's minus, a minus is a plus, right? So the cloth must have a positive charge. There's no way it could have a negative charge, because why would they both be negative? Because you just rub them. They would then instantly repel each other, right? That's kind of weird. Neutral charge also doesn't make sense, because why is one of them suddenly charged now and the other one isn't? So it has to be positive charge, then the overall charge is still neutral. It's just that it's moved around, right? Nothing's being created, nothing's being destroyed, it's just moving around. So that's all it is. It's just changing the distribution. 3.3. The negatively charged plastic rod is put near another negatively charged plastic rod that is hanging from a string. Figure 2 shows the two rods. What force is exerted on the two rods? Okay, tick one box, and then we have to defend it. Sure. So it's put near, so it's telling you that they're close together, so that you can't say that there's no force because they're not close enough. They're saying no, they are very close, so there is some kind of force, right? So when something negative is brought to something else that's negative, just in the same way that if something positive is brought to something else that's positive, you get a repulsive force. So that's how charge works. I don't really know how to explain it much more beyond that, but it's the opposite of if the rod on the string was positively charged and you brought a negative one, it would come towards, it would be attracted, because opposite charges attract, right? It's that whole opposites attract thing. So similarly, if they're the same charge, then they must do the opposite, which is repel. So in this case, it is a force of repulsion. So again, I'll just draw 3 boxes and I'll take that. And the reason is, I think the wording that they're looking for is like charges repel, right? So opposite charges attract, like charges repel. That's the rest of that saying, rule, I guess. However you want to say it. 3.4. There is an electric field around any charged object. Which diagram shows the electric field pattern around a negatively charged sphere? Wow, okay. Electric fields, sure. Fair enough. So, with electric fields, what you need to know is, so think of a bar magnet that has positive on one side and negative on the other. This should be something that everyone knows, or at least it's come across at some point. But when you draw the electric field lines, there's that sort of like really big like oval thing, right? And it goes around like that. So the question is, so there are arrows on here, so which way does it go? It goes from positive to negative. That is, it was purely convention, but that's how it was designed, right? And it keeps going bigger and bigger, but that's the point. So when we're looking for our answer here, we need to make sure that all our lines in our field go from positive to negative. So, just erase that. Go on, where's the eraser so small? Whatever. Yeah, there we go. I could have undone it, but I feel like it would take longer. So, which diagram shows the electric field pattern around a negatively charged sphere? So if it's negatively charged, all the arrows should be going towards it, which is what happens in that first one, right? You see every arrow is going towards it, that must mean it's negatively charged. So we'll just take that one off. You see, this would be true if it was positively charged, because all the arrows are coming out of it, and nothing should ever be that. It would need 2 different charges for that to be true. It would, well, or 3, I suppose. It would have to be positive in the middle, and then negative on the left. No. Yeah, it would be negative there, and then positive there. So yes, 2. It would have to be like a diagonal line. That's that would be an interesting thing to look at. Anyway. In which position do 2 charged spheres experience the greatest electrostatic force? Wow, okay. Tick one box. We've got the negatively charged ones very close together, the ones medium distance, and then very far apart. So, the question is the force stronger when things are closer together or when they're further apart? So because this is a repulsive force, right? Because like we said earlier, like charges repel, right? And this is what we've got here. These are the same charge, so they repel. The repulsion must increase as they get closer together, which that should make intuitive sense, because if you have 2 negative things far apart, then how could the repulsion be higher, right? You would feel, if you have a couple of magnets and you try and push them together, it's much harder when they're closer together than it is when they're farther apart. You can very easily bring two bar magnets with opposite charges close together at the start, and then it gets harder and harder and harder, and then it's very hard at the end. In fact, is there anything in the equation sheet about this that might help? I'm actually not sure. I guess there isn't. Okay. Well, at university at the very least, you know that this goes with the distance squared. So essentially, if you halve the distance, you quadruple, you 2 squared the force, which is times 4, right? Similarly, if you divide the distance by 10, you increase it by 100, because that's 10 squared. So in this case, it is A has the highest, greatest electrostatic force, because they're very close together, so there must be a very large force between them. 4.1. How's the time? Almost half an hour. Alright. Radioactive isotope emits different types of nuclear radiation. What does an alpha particle consist of? Okay, this is just a memory test, basically. So an alpha particle you can also think of as a helium nucleus, if that helps, but maybe it doesn't. But a helium is 2 protons and 2 neutrons and 2 electrons, but we're just talking about the nucleus. But yes, helium looks like that, right? And those are the protons or something, those are the neutrons. And then you've got the electrons whizzing around out there, right? That's helium. An alpha particle is just this bit in the middle, just those 4 things. So it is 2 protons and 2 neutrons. 2 protons and 2 electrons would be like 2 hydrogen nuclei, or 2 hydrogen atoms, technically. And then 4 protons would almost never stick together. And 4 neutrons, I guess you could stick together, but I don't think it would work very well. So, anyway, in this case, it's just presumably just a memory test, 2 protons and 2 neutrons. I don't think they're looking for any sort of, well, they're definitely not looking for any sort of workings out. You just remember it or you don't. Or you can figure it out from those other things. Like, well, it wouldn't be that, it wouldn't be that, it wouldn't be that, so I guess it's that. What is a beta particle? In this case, it is just an electron. Again, this is just a memory test. Unless you can... Oh, wow, okay. Unless, I was about to say, you start looking at these things. I know you wonder, why has it got electrons there if it's not... if one of the answers here isn't an electron, right? Yeah, I can just do 4.3 down here. Don't need to start a new one. A krypton nucleus decays into a rubidium nucleus by emitting a beta particle. What is the correct equation for this decay? Right, so you're seeing here emitting a beta particle, so you can go back. This happens quite a lot, especially in GCSE A-level papers, but even sometimes in university papers. They almost give you the answer to earlier questions in later questions. So you can go back, you can go here and say, oh, this emits a beta particle. Okay, well, I don't remember what beta particle is, but all of these have an electron. So I guess I can go back here and say, oh, beta particle must be an electron. So there's a fun tip for you. So we have here a krypton nucleus decays into a rubidium nucleus. So that means that we start with just a krypton nucleus. So the only one of these that starts with just a krypton nucleus is this one, right? So this is saying you're adding an electron to a krypton nucleus. So this is saying you're firing an electron at a krypton nucleus, right? And that's not decay. And this one, you're starting with a rubidium nucleus, and that's can't be a krypton nucleus. You can't then be talking about a krypton nucleus decay because you're starting with rubidium. That doesn't make sense. So it has to be the second one here. The krypton turning into a rubidium nucleus, and the electron there is being emitted, right? It's coming out of the krypton nucleus. It used to be a krypton nucleus, and now there's an electron, and where it was, there's now a rubidium nucleus. Cool. 4.4. Figure 5 shows an experiment to demonstrate how alpha, beta, and gamma radiation penetrate different materials. The experiment takes place in a vacuum. Okay, we've got the radioactive source, a load of concrete, and then a beam of alpha, beta, and gamma radiation. Right. GM tube, okay. Geiger meter tube, and then a counter. I'm actually not sure what the GM there stands for. I guess we'll just call it GM for now. This is a really big question, all for 3 marks. 3 different materials are used. We've got a sheet of paper, half a centimetre thick sheet of aluminium, and a 10 centimetre block of lead. Each material is placed one at a time between the source and the GM tube. Right, okay, so the question is asking what radiation are we going to see going through these various materials then, right? The GM tube and counter show whether the material has stopped radiation. Yes. So if it goes through the material, the counter should go up, and then as more preventative materials are used, the counter should go down as each radiation is being stopped. Complete table 1 to show how alpha, beta, and gamma radiation penetrate the materials in figure 5. Use the word yes and no, and part has been completed. So let's there we go. We'll just draw this table. We'll just use the words yes and no. So we'll just have N and Y. Right. So most radiation is stopped by. So the sheet of paper is the least way of stopping it, but it is enough to stop alpha, right? Which means that anything else is enough to stop alpha. Alpha radiation can only go about 5 centimeters in air. So basically anything can stop alpha radiation, even a thin sheet of paper, even a sheet of paper. So anything beyond that must stop it as well, especially because it's 10 centimeters block of lead. It can't even get through 10 centimeters of air. Here we go. So with beta radiation, that can go a few meters in air. Can go through paper, but I think aluminium should be enough to stop it. So we'll say that. And lead stops everything, right? Lead is what you need to use to block things. Or you can use, for gamma radiation, you can also use several meters of concrete, I believe. But gamma radiation is the most penetrating. You can go miles and miles in air. Yeah. Yes. I was about to say it goes through the atmosphere, but it doesn't go through the atmosphere for reasons. But if it's already in the atmosphere, there's a layer of the atmosphere that stops gamma radiation, and that's how we don't all get cancer every day, essentially. So this is what we've got. We've got alpha gets stopped by everything, the beta gets stopped by aluminium and lead, and the gamma only gets stopped by the lead. I think that's about right. It would be very harsh if the block of lead they give you isn't long enough to stop gamma radiation, but I don't think that's the case. They generally don't try and trick you like that. Not in a foundation paper, anyway. Alpha, beta, and gamma radiation have different ionizing powers. Draw one line from each radiation type to the correct ionizing power. Okay, so we've got alpha, beta, gamma, and then we've got 0, low, medium, and high. That's the weirdest rectangle I've ever drawn. So, alpha, beta, and gamma. I won't bother writing in those. So, ionizing power. So, alpha has very high ionizing power, and that's because its charge is +2, right? It's 2 protons and 2 neutrons. So it has a charge of +2. Ionizing power is also why it can't go through air enough, because eventually it's going to hit a particle in the air and ionize it, right? So if you have a very high ionizing power, you'll very easily hit something, and that's how it is, right? So beta has a medium ionizing power, I suppose. And then the question is, does gamma have 0 or low? But it must have low, right? I don't see how it would have no ionizing power at all. Because what you can do with gamma rays is you can excite an electron to the point that it leaves the atom that it was part of. But ionizing power should be low. I think they just throw in 0 to trick you. So maybe what I was saying was a bit wrong earlier about how they try not to trick you, but I believe it's just alpha is high ionizing, beta is medium, and gamma is low. I feel like you could also argue though that beta is low and gamma is 0, but I think in this case it's just high, medium, low. I don't think it's much more than that. I would be surprised if it was saying that gamma has 0 ionizing power, because it does ionize things. It just doesn't always do it. It's almost 0, but it's low. 4.6. Some sources of background radiation are natural and some are man-made. Which of the following is a man-made source of background radiation? So we've got cosmic rays, nuclear accidents, and rocks. Okay, well, the question is, which of these are man-made? Cosmic rays come from space. And when I say they come from space, they come from light years away. And men don't make things, well, humans don't make things light years away. So it can't be cosmic rays. Let me just draw the boxes here. So it can't be cosmic rays. Rocks, I mean, we can make rocks, but most rocks on Earth are natural, right? So I feel like it's probably not rocks either. Whereas nuclear accidents, we're talking about nuclear power plants, right? And especially because Chernobyl was really popular recently, I feel like a lot of people would get this. Maybe their parents had been watching it, or maybe their older cousins or whatever gotten into it. So yes, in this case it is nuclear accidents, because that's the man-made thing. 4.7. The average background radiation dose per year in the UK is 2.0 millisieverts. Sieverts? I can't remember how to pronounce that. A dental x-ray gives a patient a dose of 0.005 millisieverts. How many dental x-rays would be the same as the average background radiation dose? Okay. So, this is how many times can this be added to you until you reach 2? And that is called division. So, we're going to be dividing. So, this is a test of if you're given a problem in plain English, can you convert that into an equation, basically, and then work out that answer. So we want to know how many dental x-rays are in the average background radiation dose. So in this case, we want to know 2.0 divided by 0.005. Okay, that's our answer. This is our working, and then this is our answer. So we'll bring up the calculator. 2 divided by 0.005, and the answer is 400. And that makes sense to us, right? Because if it was a low amount of X-rays, then that would be concerning, right? Or if it was, a high number, or rather a low number, rather, like 1 or 0.1, then that would be worrying. But when they say X-rays are very safe, this is what they mean. It's that you would need to have 400 X-rays just to hit the amount you normally have in a year. So you could actually have a dental X-ray every day, and that would still be less radiation than you have just existing in the UK. And that's not to say the UK is necessarily high in radiation. That's just how much there is. Question 5. A student determined the specific latent heat of vaporization of water. Figure 6 shows some of the equipment used. We've got a power supply going into this heater, which is suspended in a beaker full of water. It even shows a little meniscus, guys. That's cute. The student measured a mass of water and put it into the beaker. What measuring instrument should the student have used to measure the mass of the water? Okay, so the question is, which of these measures mass? Or weight, I suppose, is the other question, but... okay. So Newton meter measures weight, but we are looking for a mass. So while you could technically use that, that's not what the question's asking for. A joule meter, as the name suggests, measures energy. So again, while you could technically probably use that, it won't work. A thermometer would never work. There's no amount of temperature that will tell you what the mass of water is. So it must be a balance, which, balance scales, all sort of thing, they give you a mass. So it's got to be a balance. 5.2. The power output of the heater stayed the same throughout the experiment. What type of variable was the power output of the heater? Categoric, controlled, dependent, or independent? Okay. So if the power output stayed the same, then that means that it wasn't. Well, it means it was a control variable. So how can we rule these out? So a dependent variable is something that depends on other things in your experiment. So, whereas power supply is something that we're in charge of, right? We can turn the dial on this power supply, and that will change things. So it can't be dependent, and then it won't be independent because, it's not independent of everything else, because our power supply is increasing how hot the heater gets, right? That's what that wire is doing. As the power goes up, that heat for the heater must be increasing. So it's not independent because the temperature of the heater would be dependent on our variable. Categoric variable, to be honest, I don't remember what that is. But I remember what a control variable is. And a control variable is something you control. As we have a dial, we can change what the power supply is. So we change what the power output of the heater is. Like, that's power output stays the same. Yes. I'm starting to think now with how it's worded that it's actually a dependent variable. Maybe we got that wrong. Honestly, this stuff is just only things you learn at this level, basically. No one cares what variables are called as soon as you hit university, certainly. The student turned on the heater and heated the water until it reached boiling point. The student continued to heat the water so it boiled for several minutes. The mass of the water remaining in the beaker was measured again. Give one way the beaker of boiling water could be moved safely to measure its new mass. Wow, could be moved safely, so that's what we care about. Okay. So, we want to move a beaker of boiling water. So, oven gloves, I suppose. Yeah. Heat-proof gloves, I will say, as opposed to oven gloves. Heat-proof gloves, right? That makes sense. Or if we wanted this in a real prose, right, we could say the student can wear heat-proof gloves. Yeah. You use safely to measure its new mass. How else could we move it? How else would we move it? You could use apparatus like tongs or something, but then you kind of risk breaking the beaker, so I think I'd rather just put gloves on. I think that's the safest way of doing that. 5.4. The mass of water that turned into steam was 0.009 kilograms. The heat transferred 25,200 joules of energy to the water to turn it into steam. Calculate the specific latent heat of vaporization of water given by the student's data. Use the Alright, so now we actually have to use the sheet. Choose the unit from the box. Okay, fair enough. So, we want to look at specific latent heat of vaporization. Let's go to our thing here. Let's have a look. There should just be... here we are. Thermal energy for a change of state. So that's our energy equals our mass times specific latent heat. But this is no good. We want to know what L is. So let's rearrange this into E divided by M. We just divide by M on both sides, then we just have L on one side and then E over M on the other side. And I've just swapped it the other side. Because that is exactly the same as, I'll just do a comma there, E over M equals L, right? Those are exactly the same. That's what equals means. So I've got L equals E over M, And then we've got our energy is 25200, and that's divided by 0.009, and that is something horrendously large. 25200 divided by 0.009 is 2.8 million. Okay, 2800000. Right, 2.8 million. Okay, so that's the number. What's the unit? It's either joules, kilograms, or joules per kilogram. Well, if we go back to our equation here, we know that this number here is in joules, this is in kilograms, and if joules divide by kilograms, so it must be joules per kilogram. Right, those are our answers. I was always taught to double underline my answer, which is why I'm doing that, by the way. So that in all your working, you can just point out what the answer is to your examiner, to make it easier for them to mark. Yes, so there was no trick to that. That was just, you've got some numbers, you have to find the equation in your sheet. We know which one is the correct one. This one says specific latent heat, so that's going to be the equation we need to use, because this is what we need to calculate. And then we've got our energy, we've got our mass, and we just plug it all in. 5.5. What was the source of error in the student's experiment? We either have the transfer of thermal energy from the heater to the water, the transfer of thermal energy from the surroundings to the water, the transfer of thermal energy from the water to the heater, and the transfer of thermal energy from the water to the surroundings. Okay? So, let's have a look. So, the first one here, one of the potential answers is thermal energy from the heater to the water. That shouldn't have any error associated with it. I mean, our heater is completely submerged in the water, so the heat can only go into the water. I suppose you could argue maybe a small amount will go back up through the heater, like the electronics and things, but that's very noodly. I don't think that's relevant at all compared to the real answer, which we'll get to certainly. The transfer of thermal energy from the surroundings to the water. So unless the lab we're in is very, very hot, I'm going to go with, I imagine the surroundings will not put any thermal energy into the water, because we're getting water up to 100 degrees. The air typically is not 100 degrees Celsius. It can get to 100 degrees Fahrenheit, but it's not anywhere near 100 degrees Celsius, so it's not going to be that one. The transfer of thermal energy from water to the heater. Again, the heater is always hotter than water, so there's no energy from the water going into the heater. The water isn't warming up the heater because the electricity from the power supply is doing that. So it must be the last one, and that makes sense because our water is getting very hot. The surroundings are quite cool, so there must be heat coming out of the water into the surroundings. If we had this isolated from the surroundings, then you could reduce that error, but as it is, that's all that is. Now we're on to question 6. My god, it's talking through every answer does make it quite slow. A hairdryer contains 3 heating elements. Okay, we're on to circuits now. Figure 7 shows the circuit diagram for the heating elements in the hairdryer. In Figure 7, the heating elements are represented by resistor symbols. Fair enough. That's good. It's very standard. If you need something hot, typically you just put a resistor in, because resistors get very hot. That's quite simple. The larger the resistor, the hotter it will get. Pretty sure. The 3 resistors are connected in blank with the power supply. They are connected in parallel. As you can see, these are all parallel lines, so it is parallel. I'll just put that in text. I kind of wish it wasn't such a long, standard sentence, but there we go. Parallel is the word. If there was no, if there weren't any switches, or if there was just like one wire that they were all part of, then that would be series. But no, they're all connected in parallel. 6.2. Which switch must always be closed for the hairdryer to work? Okay, so we need for a circuit to work, it needs to be a complete circuit. So you need to be able to follow the wires all the way back to the start of the power supply, right? So, must always be closed for the hairdryer to work. Well, if only number 3 is closed, then you can't get to the other side of the power supply. The question is, which switch allows you to touch the other side? And that can only be S1. S1 is the only one that can do that. Because if the other ones are closed, there's no way of jumping over this gap, so there's no way of getting to the other side of the power supply, so you can never get electricity flowing through. That's just how that is. I'm gonna have to start adding boards now. God. 6.3. Which switches must be closed for the hairdryer to work at maximum power output? Well, I suppose, so maximum power output, so we want all the energy to be going through all the resistors at once, so we want S1, S2, and S3. If they were connected in series, then you would only want S1 to be closed. It's hard to envision this in series now, but if it were in series, you would only want one resistor, because then all the power would just be going through one. But I digress. In parallel, you get more power by sending them all out. That's why parallel is useful, because you can have multiple things. Write down the equation which links energy transferred, E, power, and time. Right. Well, this is in the equation sheet, but we can just write that down now. There. That's the answer to 6.4. And then 6.5. If you don't believe me, we can go back here and find it somewhere. There we are. Power equals energy transferred over time. 6.5. The heating elements have a maximum power output of 1200 watts. The energy transferred to the heating elements to reach normal operating temperature is 3600 joules. Calculate the time taken to reach normal operating temperature and maximum power output. Right, so this is just using our equation from before, equals E over T. What we can do is rearrange this to find out time taken. So if we multiply both sides by P, we get PT equals E. And then if we divide by P, we get T equals E divided by P. The other thing you could do is just put the numbers into there and then rearrange it then. But if you just do it in letters, that's generally a bit easier. So then we have energy, which is 3600 joules. And then you've got power output of 1200. And that is just 3. So 3 seconds. Yep. And joules, watts. A watt is a joule per second. So that all the units work out there as well. Good. So this will be 1 mark. This will be a mark. So it'll be 1 mark to get it in that form. It'll be 1 mark to put the numbers in properly, and then 1 mark for the actual answer. I would assume. I haven't looked at the mark scheme, but that's kind of what I was always taught. Right, 6.6. The hairdryer has LEDs to indicate the power setting. Oh, what's the circuit symbol for an LED? Right. Well, this is just a memory test, essentially. But if you remember what a diode looks like, a diode is that. Typically, it just has the line there, where the arrow indicates where the diode is allowing charge to flow through. And LED is a light emitting diode, so it's number 2, because you see you've got the diode symbol, and then that indicates the light is coming off it. So it's a light emitting diode, it's number 2. What are these other ones? That's some kind of photodiode, I guess. That's a variable resistor, I believe, because a resistor is just a rectangle, so I think that means it's variable, having a line through it. And that I recognise, but I can't remember off the top of my head. I don't remember, honestly. I haven't done circuits like this in a long time. 7.1. We've got just about 50 minutes left. Okay, should be fine. Figure 8 shows how electricity is supplied to consumers. Yep, we've got power station over there, step up transformer, overhead transmission cables, and step down when it goes to the house. Houses. Electricity from power station can be generated using renewable or non-renewable energy sources. Complete table to show which energy resources are renewable and which are non-renewable. Tick once in each row. Fine, okay. I'll just do this. I won't write all that out. So we've got biofuel, coal, nuclear, and tides. So coal is a non-renewable resource, right? That's when we run out of coal, all the coal's gone. Nuclear is also non-renewable. It just we'll get through the uranium very slowly. So it will eventually run out, but not for many years. Tides, there are always tides. Well, I mean, as long as the moon is there, we're going to have tides. So it's essentially renewable. And then biofuel, I believe, is renewable, because that's certainly a big thing in politics and things like that, is trying to get biofuel from breaking down foods and all the rest of it. So there's always stuff to put in to make more biofuel. So it is renewable. Excellent. 7.2. Transformers used to make power transmission an efficient process. Complete the sentences. Choose answer from box. Each answer may be used once, more than once, or not at all. Okay, we'll use text for this one then, because it's but I'll just write the words, so let me just move that there. Okay. The step-up transformer increases the blank and decreases the blank. Okay, well, what do we have? We have charge, potential difference, current, resistance, and energy. So potential difference is also voltage. Step-up transformers, the step up means you step up in voltage. So it is potential difference for the first one, and decreases the blank. So it decreases the resistance, I guess, or the current. Oh, that tea's cold now. So, let's see. How does Transformers work? Oh, not the mark scheme. Not cheating. Right. Let's see. Is there anything here that can help us? So, potential difference is current times resistance. You would think that the power is current squared times resistance. Okay. And then power is potential difference times current. So it can't be... Step-up transformers don't introduce anything new into the system. So if it's increasing the potential difference, it must be decreasing the current, because the power must still be the same. Makes sense to me. Feels wrong. I feel like the whole point of doing this is you have lower resistance, because then you're losing less power as you go. But it might be... What else does it say? Using transformers decreases the blank transfer from the overhead transmission cables to the surroundings. Well, energy... I thought we were on that, but we're not. So, well, why do we bother with transformers? It's because it reduces the energy transfer from the overhead transmission cables to the surroundings, makes it more efficient. If it was less efficient, we wouldn't bother having these transformers at all. We would just have cables going straight away. But increasing the voltage makes it more efficient. I know that, at least. The step-down transformer decreases the potential difference again. It's just the opposite. Step down is the opposite of step up. It always affects the potential difference, however. Okay, so the question is, it decreases the current or resistance. I mean, doesn't it do both? Charge, it certainly won't be charge, it certainly won't be energy, it certainly won't be potential difference. So I guess it wants me to say resistance. I feel like that's right. That one actually could be wrong. I have not looked at transformers in a long time, but I'm going to go with resistance. It seems to make sense. If you increase resistance, you must be increasing how much heat you're giving off, right? So if you're decreasing the resistance, that should make things better. But if you're decreasing the resistance, do you not necessarily increase... Well, I guess no, you must increase the current. I don't know. I'm going with that. Well, there we go. We might not be getting 100, lads, but there we go. Hey-o. Use the physics equation sheet to answer 7.3 and 7.4. Write down the equation which links charge, flow, current, and time. Well, I know that, so it is just I equals Q over T with these terms. Technically, you want... Well, it says charge flow, so you want like change in time, but yeah, want some deltas in there somewhere. That's just me. The town of Hornsdale in Australia has electricity supplied by a huge battery. The battery supplies a current of 130,000 amps. My God. Calculate the charge flow from the battery in 5 minutes. Okay, so we want to know, so we have our equation, I equals Q over T, and here we want to calculate charge flow, and charge flow is Q. So if we multiply both sides by T, we get I times T equals Q, or Q equals IT. I is 130,000, because it tells us that, and we're multiplying that by 5 minutes. This is the trick, right? Amps is measured, so this equation works with seconds. So we've got 5 minutes, and we have to multiply that by 60 to get it into seconds. So 5 minutes is 300 seconds. So I'm making sure I'm not going off the side. So we get our calculator out, and we do 130,000 multiplied by 5 minutes, but we would times 60 to make that seconds. Just 39 million. There we go, close enough. And then choose the unit from the box. We're talking about charge flow. Charge is measured in coulombs, so it's coulombs, which is you represent with a C. Newtons is an N, watts is W, but watts is for power, newtons is for force. This isn't either of those, this is charge, which is measured in coulombs. So that's the force, that's the unit we have to do. 8.1. We've got 40 minutes left to do 4 questions. Alright, kind of got to pick it up a bit here. A student investigated the insulating properties of 2 different materials. The same thickness of each material was used. Figure 9 shows some of the equipment used by the student. We've got a thermometer, we've got a lid, a metal can, some hot water, and insulation. The student used 2 different types of thermometer to measure the temperature changes. Figure 10 shows the reading on each thermometer. So we've got one that says about 67 and that one says 67.4. Cool. What is the resolution of thermometer B? 0.1, 0.4, 67.0, 67.4. Resolution is how accurate, how precise you can measure things. In this case, it is 0.1. So if the temperature changed by 0.1 degrees, we would be able to tell. Right? So the resolution is 0.1. That's all that means. All of these other ones are just to trick you. It's just that's all it is. 8.2. Complete the sentence, choose the answer from the box. We've got smaller, the same, or bigger. Okay. Our question is, thermometer A has blank chance of being misread than thermometer B. Well, I'm going to say a bigger. And the reason for that is, if you look at the thermometer A, we know that it's somewhere between 67 and 68, right? But we can't tell where. However, this tells us this is 67.4. So this is the whole analog versus digital thing, basically. So, yes. So thermometer A has a bigger chance of being misread than thermometer B because the resolution is lower. Basically, that's the reasoning for that. Or what I would say is the reasoning for that. 8.3. Figure 11 shows the results. Cool. The mass of water used was 0.12 kilos. The specific heat of water is that. Determine the total change in thermal energy when material X was used. It's a pretty melting stream. Exactly. We're doing some GCSE papers. And I've got currently 37 minutes to do the next few questions. So I have been explaining it though, going through it in excruciating detail. So if you like that, want to stick around, feel free. Determine the total change in thermal energy when material X is used. Use values for figure 11. I will do. Thanks, Galanthus. So, total change in thermal energy. Right, physics equation sheet. Here we go. We want something that has specific heat capacity of water and thermal energy. So, here we are. Change in thermal energy is that. So, delta E equals mc delta theta, where theta is our temperature change. Fine. The total change when material X was used, so we've got that and that. So it's, can you read a graph is the question, essentially. So we've got delta E. We know what our mass is, because that is 0.12, as it tells us just there. C is our specific heat capacity, which it tells us there is 4,200. So that's just 4,200. And now we need our change in temperature. So here we have our temperature. At the top it's 75, so I'm going to do this in brackets. We've got 75 minus the bottom one, which is, if we follow that line, right in between 60 and that is 62.5. So in between 60 and 65 there are 10 squares, so that is 62.5. Okay, not written very well, but I said it, so. So, what you can do is just do that first, and then replace your brackets with the actual number. That's perfectly fine. But if you want to do it all on the calculator, the first thing you can just do that first. 75 minus 60.5, and it's 12.5. Times that by 0.12. Which is our mass, and then times it by 4,200, and we just make sure that we multiply every number. And total energy change is 6,300 joules. If I had this paper really, I would get my ruler out and draw a line all the way there to the other side, so that I know exactly which box it stopped at, and I can count the boxes and make sure I know exactly. But you can see there, it's very clearly exactly halfway between 60 and 65. So yeah, total change thermal energy is 6,300 joules. Nice. 8.4. There's an anomalous result in figure 11. Wow. Draw a ring around the anomalous result. Oh, this is going to be difficult. Okay. So which of these doesn't look right? Well, it looks like that one, right? Because it's not along our line at all. So, God, I don't know. I guess I'll just draw the graph, and then there's that X up there, and I'll circle that. There we go. And that's our other one. It's kind of hard for me I can't edit the PDF directly, so we'll leave it like that. 8.5. Give two conclusions that can be made from figure 11. Well, material X keeps it warmer, I suppose. What are we actually trying to figure out here? To measure the temperature changes. The student investigates the insulating properties. Okay, so we're interested in how well they insulate. So in that case, material X is the better insulator because the temperature stayed highest longest. So X is the better insulator. That's one thing we can say. And then I'm not sure what else we want to say here. We have two conclusions made from figure 11. Right, but it's specifically this one. Two conclusions. What would the other conclusion be? We're not trying to figure anything else out from this equation, are we? From this, the same thickness was used. This is kind of stumping me. What's that meant to... What's the second conclusion? It's going to be something really dumb, but unless what it means by conclusion is just what can you get from the graphs. I don't know, that's kind of strange. You have two conclusions that can be made from figure 11. What do you mean by two conclusions? That's a really bizarre question. I mean, the entire thing is X is the better insulator. That's got me. Alright. I suppose we can just say... Maybe what it wants is X... There's nothing with this sort of curve. And the effects are... could it be? I don't know. I don't think it's that advanced. So these papers are only for 16-year-olds. And this is the foundation paper. So I think it's simpler than what I think. So I think it's more that the two conclusions are just how low did the temperature get over the 10 minutes. So I think this is just X temperature D. Never took physics. Okay, well, fair enough. So I believe this is just like using X, temperature goes down to 62.5 after 10 minutes. And then it would just be the same using Y, temperature goes down to 57, looks like to me. 57 after 10 minutes. I think that's what it's after. But I mean, I would just say the overall conclusion is that X is the better one, but hey. I wouldn't be surprised if it was just something so mind-bogglingly simple I just didn't think of it. But 60, yep. Yep, this is GCSE. This is what we do. This is the foundation GCSE. So you can see a foundation tier. So this is the most basic physics paper that you do. For AQA, anyway. There are different exam boards, but this is the AQA exam board. Right, we're on to April. Another student investigated how the thickness of the insulation affected the rate of cooling of hot water. Shows some of the equipment used. So we've got some insulation here in a metal can, hot water, a lid, and tomatoes, with thick insulation on that side and thin there. Fair enough. How would using thick insulation affect the rate of cooling of hot water compared with using thin insulation? So, I forgot to put in 8.6. The rate of cooling would be higher, lower, or wouldn't change. Well, I mean, if the insulator was very good, it wouldn't matter. But I'm assuming it's not going to be a crazy good insulator. So using more insulation means that the water is more isolated from its environment. So that would mean that the water would cool slower with more insulation. So the rate of cooling would be lower. That's what I'm going to go with. Because I'd be surprised if it didn't change. That would be true if it was such a good insulator that you only needed a small amount. But I think the point of saying thin versus thick is the surprise way. Be specific, yeah. Exactly. But yeah, I think we can safely say that because it says thin and because it says thick, there's a reason, right? There's a notable difference between the two. So yes, I chose, yeah, rate of cooling be lower. I'm going to stick with that. 8.7. Predict how using thick insulation would affect the temperature of the water after 10 minutes compared to using thin insulation. Right, so this is just checking you understand what you said just earlier. So in this case, the temperature would be higher because the water is starting off hot and it's cooling down. So because it's cooling down slower, it will still be hot. It'll still be hotter at the same time, after the same amount of time. Yeah, because if it was lower, then it means it's cooling faster. If it's the same, it was cooling wouldn't change. So as long as you're consistent, I think you get that mark. So even if you got that earlier one wrong. 9.1. All right, we've got 3 questions left. Got 27 minutes. Figure 13 shows a wind farm. Wow, look at all those wind farms. Look at all those windmills. The mean power output is 696 megawatts, which is enough power for 580,000 homes. Calculate the mean power needed for one home, and then give your answer in watts. So, this is a check of, do you know what megawatts means? Mega, as a term, means a million. So it is 1M is 1 million. So that means that 696 megawatts is 696,000,000 watts, which is a lot. So that would be 1 mark, I believe. So it actually means something. Yeah, surface loss paid off. Exactly. And that's enough for 580,000 homes. So the mean power for one home is just that, 696,000. I'm just getting it down as quick as I can. Over 580,000, which is, you are allowed scientific calculator for these, so that's what I've been using. 696,000 divided by 580,000 is 1,200 watts. Okay, and generally the answer number is always a nice number. That's how you can tell that you've done it correctly. If it was like 1,156.79, I would have gotten something wrong. It's a fun tip. 9.2. On one day, the demand for electricity was 34,000 megawatts. Okay, that's not right. That's so much higher than what this one wind farm can do. It's just 2 reasons why wind power was not able to meet the demand. Okay, well, 2 reasons why wind power is not able to meet the demand. So the mean output is 696 megawatts. Why wind power is not able to meet the demand? So, I mean, 696 megawatts is less than 34,000 megawatts. So, I mean, that's one obvious reason, right? It wouldn't be able to. The mean is much lower. But then I suppose it may be looking for more realistic answers, like maybe not much wind that day as one answer. So, you know, the power output was lower from the wind farms, wind power in general. Well, yes, okay. Fair enough. Maybe not much wind that day. That would affect all the wind farms. And then, I don't know, I guess, why wind power is not able to meet this demand? Not much wind. What else would affect wind farms in general? I don't really know. What would the other reason be? What else affects wind farms? There's such a some of these questions. The later questions have been a bit strange. A lot of the earlier ones are very simple. Too much wind. Yeah, I'd be surprised if that was. I mean, yeah, we don't really get like hurricanes and things, right? So I don't think our wind ever gets so high. Does that? Off the coast. No, I was trying maybe something to do with the water level or something of the sea, but I don't think it would be that. So there's 2 reasons why wind power is not able to meet the demand. Maybe just not possible for wind, to ever generate enough. From wind power. So maybe I think that's enough. I think that's distinct enough of a reason. I think maybe the wind power wasn't its maximum, and then the other reason is even if it was maximum, it still wouldn't be enough to hit 34,000 megawatts. I think that's good enough. I think we'll go with that. Especially because we're running out of time. We've only got 23 minutes left. I'm not going to hold myself too much to that, but it's fun. It's a good way of bounding it, I guess. Some of the energy from wind used to rotate a wind turbine is wasted. As an engineer oils the mechanical parts of a wind turbine, explain how oiling would affect the efficiency of the wind turbine. Okay, so this is, why do we oil things, basically? Engineer oils the mechanical parts, so oiling reduces the resistance in the mechanical parts. Reducing resistance means less energy is expended. It is expended as thermal energy, I guess. It's thermal energy? Boom. Yes. Oiling reduces the resistant mechanical parts. Reducing resistance means less energy. I feel like that's worth 3 marks. Would affect the efficiency specifically. So, I guess just that means more of the starting energy turns into electrical energy, I guess. That sounds fine. Maybe that's, I don't know, that might be close enough. All these wordy questions now, all the earlier ones were just numbers, basically. In most homes in the UK, there are many different electrical devices. Very true. Explain why people should be encouraged to use energy-efficient electrical devices. Okay, that's kind of... I love the bits where it gets, like, really political, almost. It's like, oh, now we're talking about global warming and things. Use energy-efficient. So, I mean, to reduce demand, which means UK is less reliant on non-renewable. We did one of the questions earlier was talking about non-renewable things, so non-renewable energy sources such as coal, oil, which contribute to global warming. I don't know, something like that. I'm assuming it's going for a kind of global warming / making sure that the power that we have is the power that we generate is enough to actually keep the UK going. So reduce demand. So I guess the other point is just can I go back to click on that? Yep, good. Let's know. Also, so there is enough power for everyone in the UK. There we go. I think that's enough of a second point. So there's enough power for everyone, and so we're less so we're less reliant on coal, oil. Sure, that makes sense. Okay, that's what one just did, and we're on question 10. Excellent. Still 20 minutes to go. 10.1. Figure 14 shows a rock found by a student on a beach. Oh, what a lovely rock. All the pictures are always in black and white, so you can like barely see anything. To help identify a type of rock, the student took measurements to determine its density. Okay. Wow. Okay. Just design an experiment to determine the density of the rock. Okay. That's interesting. That's a fun way to do it. I suppose we could go full Greek. Just get a water bath and just plunge it. So the hard part is measuring volume. So I guess the easy thing to do. So we'll do the easy bit first. So to measure density, need mass and volume. Okay, because that's what the equation for density is. It's mass divided by volume. So to find mass, put rock on a balance. You know, some scales, some balance, scales. Back to brain melting. So getting the mass is easy, right? You just put on some scales and it's whatever, 200 grams or something. Now to find the volume, what we can do is, so back in Greek, so there's a whole thing of if you put a rock in a bath of water, the water level rises. So there's a whole thing on buoyancy and things. So that can be a way of finding volume, is by looking at how much the water level rises, or if you have a completely full beaker and you put something in it, all the water will spill out of the beaker. So if we measured how much water came out of the beaker after putting a rock in, that would give us an idea of what the volume is, because we know the density of water, we know the volume, and we can work out the mass of the water that comes out. So that's a way to do it, I suppose. Fill a beaker completely with water. Okay, good, I'm not going to that. Then put rock in beaker. Measure mass of... Oh, I suppose we can just put the beaker in and then put the rock in the beaker and then take the rock out and then measure... Yeah, measure mass of water that came out of beaker. Ooh, it came out of beaker. Which we could do by deduction if we need to. So we can measure the beaker beforehand and then measure the beaker after, and then that change in mass is how much water came out, right? Rather than try and capture all the water that comes out and measure that. I feel like that would be more difficult. Then calculate, so we know the mass that came out, so we know how much volume it is because the volume should be the same. So use that mass and known density of water to find volume, and then we have a volume, we have a mass, then calculate density. Mass divided by volume. Yeah, I feel like that would work. I think. And I feel like that's enough to cover all that if I were to write it out properly. Amazing, it made sense. Excellent. My degree wasn't worthless. I like to think. 10.2. Right. The student determined the density of the rock to be that. Ooh, look, we've got an error. Excellent. What are the maximum and minimum values for the density of the rock? Well, we've got plus minus 0.1, so the maximum would be plus and the minimum would be minus. Yeah, that's just what plus or minus means. So we've just got, you just got to make sure that you don't mess up with decimal places. So you've got 2.65 as the maximum and 2.45 as the minimum, because that's just what that means. So that makes sense. 10.3. Table 3 gives density of 5 different types of rock. We've got basalt, chalk, flint, sandstone, and slate, all with good errors. Which 2 types of rock could be the type of rock the student had? Okay. We've got basalt or chalk or flint, flint or sandstone, and sandstone or slate. Well, we know that density of the rock is somewhere between 2.45 and 2.65. So, basalt is between 2.8 and 3, so it can't be anything to do with basalt, so it's not the first one. Chalk can go up to 2.5, so it could be chalk. Flint can be 2.5 to 2.7, so it could be flint, which chalk or flint is the second one, so I'm going to say it's probably that one, but let's double check. Sandstone can go up to 2.4, so that it can't be that, that's too low. And then slate can go down to 2.7, which is still too high, so it can't be that one. So it's chalk or flint. Nice. 10.4. The student only took one set of measurements to determine the density of the rock. Explain why taking the measurements more than once may improve the accuracy of the density value. There's a, this is error propagation, I suppose, which is definitely too advanced if I go too much into it. There's a whole, like, adding things in quadrature, which is not a word I expect a 16-year-old to know, certainly. Only took one set of measurements to determine the density of the rock. Why taking measurements more than once may improve the accuracy? So, to reduce error, one can take multiple measurements, but what do you do with those measurements? And take the mean, of those measurements. Why does it go off the board? That's so stupid. So you take the mean of your measurements, so you add them all up, divide by the number of measurements you took, and that any sort of smaller errors get sort of cancelled out almost, because maybe one of those you measure as 2.65, another one you measure as 2.45, then you get one as 2.57, and then there's like a 2.3 randomly. All right, but those, if you then average those all out, you get it much more in the middle, which is what it's hovering around. So that gets you closer. So which gets you closer to the true value. So you basically take the mean, which gets you close to the true value. I guess I should say because small errors, or the effect of errors gets reduced, because effect of small errors gets reduced. I suppose we'll say that effect of small errors gets reduced. Obviously, if you measure wildly different numbers every time, then averaging out won't necessarily help you very much. But for small errors, it works very well. Final question. Wow, we've got 11 minutes to answer it, and it is question 11. An engineering company has invented pavement tiles. Amazing. That's revolutionary. Oh, that generate electricity. Oh, okay. As people walk on them. Figure 15 shows someone walking on pavement tiles. Cool looking pavement tiles. Use the equation sheet to answer the next two questions. Meh. What equation links current, potential difference, and power? Do you know this off the top of your head? It's a good question. I believe it's that. Voltage times current. But we've got our data sheet here, and here we have power equals potential difference times current. P equals VI. So of the boxes, it's that one. It's helpful that they give you that, but I feel like, I always wrote it as IV, so VI is, I don't really like that, but fair enough. When a person walks on a tile, a potential difference of 40 volts is induced across the tile. The power output is 4.4. Calculate the current in the tile. Okay, well, we've got P equals IV. We know what P is, we know what V is, but we want to find I, which is the current. So we can rearrange that if we just divide by, I consistently. If we divide both sides by V, we get I equals P over V. It gives us that P is 4.4 watts, so put that in, and then the potential difference is 40 volts. So that is 0.11 amps. Yep, and hopefully, you can see that good. But I'll double check because we do have our calculator here, but I'm pretty sure that's correct. Yes, 0.11 amps. Excellent. 11.3. Yeah. Use the physics equation sheet. Why does it not just say use the physics equation sheet to answer or whatever? What equation links efficiency, total power input, and useful power output? So efficiency is useful power output over total power input, right? Pretty sure that's right, but we've got our physics sheet. Useful output and total input. Yeah. All the energy you put in, how much of that becomes useful? That's your efficiency. So of the three boxes, it is the first one. Yes, good. Just double checking, but I wasn't ticking the wrong box there. And 11.4. How many parts are there to equation? Oh, right. No, this is the last question. Hey, okay. The tiles are used to power LEDs. Wow. Light emitting diode lights. Sure. An LED has a total power input of 4 watts and the efficiency is 0.85. Calculate the useful power output. Okay, well, our efficiency, which I'll just call E, equals the useful power output. So our efficiency is 0.85. Yes. Our useful power output, which I guess I'll do, total power input. Oh, God. TPI, why not? Total power input is 4. So we've got E equals useful power output over total power input. And we want the useful power output. So we multiply both by the total power input. And we got UPO equals E times TPI. It looks horrible, but there we go. A UPO equals 4 times 0.85, right? Which is nice and simply 3.4 watts. Yes, watts. We are on watts. Good. But again, just double check that with calculator, just to make sure I'm not crazy. Yes, 3.4. Cool. And we're done. Hey! We split. We just about got there in time, with about 6 minutes to spare. So now we've got time for marking, and I'm probably going to have a few minutes break, because my, well, when I say break, I mean not like leave, but break from using my brain for a bit. There we go. Let's do some marking. Let's see how we do. No, you're missing the eye level here. Divide the circumference of a pumpkin by its diameter. You get pumpkin pie, right? God. Woo! Yeah. That's an old joke. Right, we've got 21 boards to go through. Okay, foundation tier mark scheme. Here we go. So, this is just how to use the mark scheme, but I mean, it gives us the answer, and we see if that's right or wrong, right? Blah blah blah. Obviously, some of these are a bit harder because the free text answers, you can get some marks even if you don't write the correct things. So, question 1, I guess because you went around, we'll bring it out. So, this is talking about as a boy falls, what energy decreases and what energy increases, and you've got these different kinds of energy. So he decreases his gravitational potential and he increases his kinetic energy, which is correct. So that's 2 marks there. And then the next one was just a calculation, right? Yeah, so it was calculate the energy stored in the springs of the trampoline, or in one spring to start with. So that came out as 13.5 joules, which is correct. And yeah, we got one answer for writing out the equation just with the numbers. So that's good. Then there are 40 springs, and it's just 40 times our last answer. And then it says that allow their answer from point 1. So if you got that early one wrong, if you just multiply by 40, you still get the full mark for that question, which I've always liked about these kind of papers, is that even if you get an earlier part wrong, if there's a later part that relies on the answer, if you still do the method correctly, you get all the marks, which is really nice. The kinetic energy as he lands, so the boy bounces and he loses kinetic energy, and then it's just how much energy does he have. So this is just 45% of 600, which is that, yep, which is the same as that first there, and now it's 270, so very good. 1.5. Why is the kinetic energy less than when he landed? So why does he reduce his kinetic energy after bouncing? And that's because energy is transferred to the surroundings, which is correct. Yes. This was probably the first one that gave me pause for thought. You're measuring the height of stairs. What measuring instrument should you use? And I was thinking, well, a tape measure would probably be best, right, in terms of length, because most rulers that you deal with are only like a meter or so. But I think a ruler is fine. I'd be surprised if it was like a really specific measuring thing. I think a ruler should be fine. Tape measure or meter rule. Okay, cool. I did actually say both. I crossed one out because I didn't want to just put both as an answer. Allow ruler. Yeah, ignore meter stick. Interesting. But you could say meter rule. Sure. So you have to specify that it is a meter long ruler, I guess. Fair enough. The height of the stairs was 1.7, the mass was 50, blah blah blah. Calculate the change, gravitational potential energy, so it's just putting all those numbers into an equation. So as you see here, 50 times 9.8 times 1.7, which is correct, and then 833 joules, which is correct as well. Excellent. So you can see a lot of a physics paper is just maths. It's just, can you put the numbers into an equation properly and then use your calculator? A boy ran up the stairs and did a bunch of work, and it took that amount of time. Calculate the power of the boy. So again, this is just put the numbers into the equation, 1,800 divided by 1.44, which it says there, and then 1250 watts. Excellent. Which stopcock was used to measure the time? So this was talking about precision. So it was 1.44, so it can't be one that can't ever say 1.44, which is both of those. So it has to be C, which does say there, stopcock C. So that's great. Calculate the kinetic energy of the buoy at the top of the stairs. Again, you've got the mass, you've got the speed, you just put it all into the equation, and you get a half times 70 times 2 squared, and then that is 140 joules, which is correct. Excellent. Okay, we're 100% after 2 questions. That's promising. Figure 3 shows a plastic rod being with a cloth. Okay, then we go into charge and electric things. Each answer, so you have to use electrons, protons, and neutrons to fill in these words. The plastic rod gains electrons, and the cloth loses electrons. So it should just say electrons for both, which it does. I wrote it as E- because I couldn't be bothered bringing the text out, but yeah, they are electrons. Move around. What charge is left on the cloth? So because it loses electrons, minus and minus is the plus, it has a positive charge, which is correct. Yes. Nice. 3.3. A negatively charged plastic rod is put near another negative charged rod. What force exerted? We've got attraction, repulsion, or no. Well, there's repulsion because like charges repel. I'm marking that correct without even checking. It's force repulsion. The rods have the same charge, or the rods are both negatively charged. Yeah, so like charges repel. I mean, that's what that means, right? When I say like charges repel, I'm saying the rods have the same charge, so that's fine. I probably should have written that as a full sentence and said because both things have the same charge, the same kind of charge, but there you go. So 3.4, yeah, we go into electric fields. So the important thing with electric fields, I'd drawn a bar magnet and erased it later, but all the lines in electric field go from positive to negative. So you can see here in this one, all the arrows go towards the negatively charged circle, so that's the correct pattern, which is correct. Yeah, that would be true. This one would be true, all the arrows going away if it was positively charged, but because it's negatively charged, all the arrows go towards it. That's just how electric field lines work. In which position do 2 charged spheres experience the greatest electrostatic force? It's when they're close together. So because it's repulsion, as you bring them close together, it gets harder to overcome it. So that's where the greatest force is. So it was A, should be A. Yes, A. Good. I'd be surprised if that was wrong. Because yeah, you can think of, it's very easy to put the negatively charged things close together when they're far apart, but it's much harder to do that same distance when they're closer. The radiation section. What does an alpha particle consist of? It is 2 protons, 2 neutrons, or also a helium nucleus. And that's basically just memorization. You just have to remember that's what an alpha particle is. There isn't really a way you can figure that out unless you know other things about alpha particles, I suppose. What is a beta particle? Similarly, you just kind of have to know it. It's an electron. Although in this case, in 4.3, you are told that this nucleus decays by emitting a beta particle. And if you look in the equations, it has an electron in the equations. So then you can then go back to the earlier question and go, oh, well, it must be an electron. Because this one says beta particle, it has electrons in it. What's the correct equation for decay? Well, you're starting with just a krypton nucleus, and then you're decaying into other stuff, and you emit an electron, so it has to be the second one. Which it does, which it says right there. Excellent. So that's why that one's correct. 4.4. Okay, and this is about how far alpha, beta, and gamma radiation can go through, or what they can go through things. So alpha particles can only go about 5 centimeters in air, beta particles can go several meters, and then gamma can go kilometers in air. With alpha, you can stop most of it with just a sheet of paper. Basically anything will stop alpha particle radiation, so I've got yes for all three, all these different materials. Beta can go through paper, as it actually gives you. I'm pretty sure aluminium can stop it, but I don't actually know that. But I feel like it wouldn't put it there if it didn't. So I said yes, it got stopped by that. And then gamma particles can basically only be stopped by lead or like meters of concrete. So that's what I'm expecting it to look like. And we've got yes at the top, and no yes, and then no yes. So that is all good. It's 3 marks. Wonderful. 1 mark for each correct row. Okay. Allow ticks and crosses. Fair enough. Well, I said Y and N because good enough. This one's the next one to give me pulse of thought. But I'm pretty sure I've got it right. So you have to line up the radiation type with how well it ionizes. Alpha particle definitely has high ionizing power. That's why it can only go a few centimeters in air, because then it interacts with the air very easily. Beta particles, you can avoid a lot of air for a while, but eventually you'll hit something. And then gamma radiation can just go through kilometers and kilometers of air before it hits something. But it should still have a low ionizing power. But it's just the 0 threw me off a bit. But I think it should still be low. Yes, good. So we've got alpha to high, beta to medium, and then gamma to low. Good. Okay. Yes. Good. Okay. Good. The 0 is just there to throw you off. Some sources of background radiation natural, some are man-made. Which is man-made? It's nuclear accidents, because cosmic rays are from space, rocks were here before us, and they'll be here after us. It is indeed nuclear accidents. So, no upsets just yet, but we've still got a few questions to go through. The average radiation dose is 2, and then a dental gives 0.005. Calculate how many x-rays would be the same. It's just that how many of those go into that. So it's 2 divided by 0.005. 2 divided by 0.005, which is that, and then 400. So you've got a number, a mark for the actual number and a mark for showing you're working. Now here we are, question 5. Measure the mass of water and put it into the beaker. What measuring instruments do you use to measure the mass? Well, which of these gives you an answer in kilograms? It's balance, or grams, I suppose. Joule meter gives it in joules. Newton meter gives it in newtons. Thermometer could never measure mass. It gives you temperature. So it's got to be a balance, which is correct. The power output of the heater stayed the same. Oh, yes. This one, I'm pretty sure, is control. Control variable. Types of variables is not something I've looked at in a long time. It's certainly not well, I don't know, yeah. So you have your power supply and you're setting the voltage of the power supply. So now that I think about it, it may actually be a dependent variable, because it depends on what voltage you're setting the voltage, and that's the control variable. And then so the temperature of the heater is the actual dependent variable. Now that I think about it, I kind of want to change my answer. But you're to the end of you are controlling the temperature of the heater. So it's still a control variable in a way. This one I feel like was kind of tricky. I feel like it was a bit mean, but I don't know. Maybe the actual definitions of these different variables makes it more obvious. But I don't know. I said control variable. I wouldn't be surprised if it's dependent. I actually can't remember what categoric variable is. So, I mean, if it's that, then fair enough. Control variable. Okay, good. So they're not. So I did get that right. So it's not super. It wasn't super pedantic, because I feel like you could have been moved. Although dependent variable might depend on actual processes rather than setting a variable. Anyway, I don't know. Anyway, we got it right. So I'm still doing well. Give 1 by the beaker of boiling water could be moved safely to measure its new mass. So I just said heat-proof gloves. I did think maybe you could use tongs, but then I'd be a bit worried about breaking the beaker because you can't. You could quite easily put too much force into that. But, tongs, gloves. Yeah. Okay. Good. It does say you could use tongs or a heat-proof mat or other sensible methods. So using a cloth, for example, or you could just wait for it to cool down. Yeah, that's probably the safest. Just wait for it to cool down. It's not moving a beaker of boiling water, but it's moving the water, isn't it? 5.4, mass of the water was blah, 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 blah. Calculate the specific latent heat vaporization. So that's in the equation sheet. It's just E equals ml, and you want to find L, so you rearrange it to L equals E over M. Put in the energy, put in the mass, and you get the number, and then you just have to double check the units. So that should all be fine. We've got that, yep. Well, okay. So yeah, it's 2.8 million. We have L equals 25,200 over 0.09, and I think because we have that, that's the first one, basically. So I didn't put the numbers in first, I rearranged the equation, then put the numbers in, but that's the same. And then it is joules per kilo. Good. What was a source of error? I said it was the last one, which is the transfer of thermal energy from the water's surroundings. Yeah, I mean, it's not insulated at all, and the water is very hot, surroundings are not very hot. So you would expect it to radiate heat, which it does. Excellent. 6.1. Okay, we've got electric circuit. Complete sentence, the three resistors are connected in blank, they are connected in parallel. They're not in series, so they're connected in parallel, which is correct. Which switch must always be closed for the dryer to work? Well, you need to access from one side of the power supply, you need to go to the other side of the power supply, so S1 needs to be closed, which is correct. And then, which switches must be closed for maximum power output? So you want power to be going through all three of the resistors in parallel. So you need all the switches to be closed, which is the third box. S1, S2, and S3, which is correct. Write down the equation which links energy, power, and time. Power is energy divided by time. Okay, well, yes. I mean, it's the same, that's the same thing. Energy is power times time. What's the one? Is the one in the? I actually didn't use the sheet for that because I knew it, but yeah, it says power equals energy over time. So why does the mark team have to get it rearranged? Anyway, whatever. It's the same equation. So heating elements have that. Blah blah blah. Calculate the time taken to reach normal operating temperature. So this is just rearranging your equation to get 3,600 divided by 1,200 equals T, which equals 3. And because I'd rearranged it earlier, I had that, which is exactly that, just with the numbers in. So that's the other mark there. What is the symbol for an LED? So this is what a diode looks like. So if you know that, then you should know that a light emitting diode should probably have that symbol in, which it does. So you can see you've got the light coming off it. I don't remember what that one is, but I'm pretty sure that is some kind of photodiode. It's like taking light in and it's a resistor, and then that's a variable resistor. But here we have a diode with light emitting off it. So it's the second one. And then here we are, electricity. So biofuels renewable, coal isn't, nuclear isn't, and tide is renewable. That should be what it says there. Correct. Good. That's 2 marks. Transformers used to make right. Okay, this was another one. I haven't looked at transformers in a long time, so I know that step-up transformers increase potential difference, but I'm pretty sure it decreases resistance. It's either resistance or current, and I would think it's resistance, because that makes more sense to me, because it decreases the energy transfer from cables to surroundings, and step-down transformer decreases potential difference. But we may lose 1 mark here. It is current. I actually got that one wrong. Oh, I'm sad. It is current. Got the other ones right though. Potential difference, energy, and potential difference. But no, it was current. Fair enough. Okay. I haven't looked at transformers in a long time, so fair. I guess it's talking about specifically about the transformer, and in that case there's no way for it to affect the resistance directly. So -1 mark. Didn't get 100%. That's sad. 7.3. Write down the equation which links charge flow, current to time. It's that yeah, Q equals IT or I equals Q over T. I mean, it's the same equation, just rearranged. The town of Hornsdale has a huge battery, and this is just how long battery supplies has a current to that. Calculate charge flow after 5 minutes. So the trick here is just making sure that you turn the 5 minutes into seconds by multiplying by 60. So yeah, time is 300 seconds, which I've put there. So that's 1 mark. Q equals 130,000 times that, which is the other mark. So Q equals that long thing. And then coulombs, yes, is the unit, because you have to choose coulombs, newtons, or watts, and it is coulombs for charge. Newtons is force, and watts is power. Question 8. 8.1. What's the resolution of thermometer B? It's 0.1. So if the temperature changed by 0.1, we'd be able to tell. So that's the resolution. Yes, correct. Number 2, thermometer A has a blank chance of being misread. Well, it's got a bigger chance of being misread because you can't tell if that's 67.4 or 67.5 just from looking at it. So it has a bigger chance of being misread, which is correct. Okay, here we go. This this is the easier one. So this is just the total change in thermal energy. So that's just using your equation, putting the numbers in. So yeah, identify 75 and 62.5, which I did. So yeah, delta theta is 12.5, fine. E equals 0.12 times all that, so mark that, and then 6,300 joules. Yeah, all that was fine. There's an anomalous result. Well, yeah, it's that one above the line, right? Point at 7 minutes for material X. Yes, good. I mean, I wasn't going to draw it out perfectly, but it's very obvious which one I'm talking about. Okay. Sorry, there we go. 2 conclusions, right. So, let's see if we get these marks then. So I think it's just that. Oh no, okay. Right. Interesting. The rate of cooling decreases time. Oh, that would have been, yeah. That would have been a good thing to say. The rate of cooling decreased. Yeah. Okay, well, I'll give myself 1 mark for saying what I said earlier about X being the better insulator, because that is one of the marks. But yeah, just a -1 there as well then. I didn't realize. So water wrapped in material X cooled slower. Okay, so I guess that's kind of what I said there as well. So, okay, if I hadn't rubbed out, you know what? I'll be generous to myself and say I didn't erase what I said before, and I still said X is the better insulator, because I did write that. I just got rid of it because I thought it was too the better insulator. Yeah, because that is true. So yeah, I shouldn't really have deleted that before. So I guess this is just saying cool more slowly. Yeah. Which is basically what that is saying. So I'm going to be generous and give myself that. Yeah, let me just tick that. 8 points. I mean, we've already not got 100% anyway, so whatever. So I said the rate of cooling would be lower because it has more insulation, which should be correct. Yes, the rate of cooling is indeed lower. Good stuff. 8.7. How using thick insulation would affect temperature. The temperature would be higher because the cooling is lower, so it stays at a higher temperature. Temperature would indeed be higher. Good. 9.1, yeah, this is just simple maths, just 696 million divided by 580,000. So yeah, 696 million and 1,200 watts. Good. On one day, it says 2 reasons why wind power wasn't able to meet demand. So yeah, maybe not much wind, and maybe the total capacity is just never possible. Wind is unreliable. Okay, allow it was not windy. Yep. Okay. Wind turbines don't turn when the wind is too strong or weak. Alright, there you go, Galantis, you were right. I was potentially one. There are not enough wind turbines. Yeah, that's basically what I'm saying there. Energy from wind may not be enough to generate, yes, which is what I said. You could also have had, may have been offline. Good job. Allow some of them may have been off for maintenance. That's good. That's a good realistic one. I like that. Ignore weather conditions unqualified. Nice. 9.3. Some of the energy from wind is wasted. So yeah, oiling reduces. Right, let's have a look. What do we have to get? The efficiency would increase. Well, yes. Does it not? Oh shit! It did say would affect the efficiency. I didn't actually say the efficiency would go up. Probably should have said that. Because the amount of energy usefully transferred would increase. Yep. More of the starting energy turns into electrical energy. Yep. Because less work is done. Because less friction. Yep. Reduces resistance. Yes. So, but I didn't actually say the efficiency would increase. That's actually a -1 there as well. That was, yeah. I just blanked. So it said affect the efficiency. Should have actually said how it impacts the efficiency. That was bad. 9.4. In most homes, there are many difficult. Why we should use energy efficient. So minimize demand. Yep, reduce demand. And is that fossil fuels? All right, so waste less energy, need a lower input. Okay, so I guess I actually got -1 there as well. I didn't actually say that they're more efficient, so they waste less energy, which I feel like isn't a strong enough point to make, but fair enough. That's how it is. That's how it is. More efficient devices need a lower energy input. That's kind of a good way of putting it, I suppose. So, ignore useless electricity. Yeah, I don't know. Yeah. No, okay, yeah, I guess just -1 there as well. This is why the free text answers are always so harsh. It's very easy to feel like you've written enough points, but not necessarily. 10.1. What is the method they put in the mark scheme? Okay, so 5.6 just it would lead to. So this is judging on how well the examiner would know what to do. So measure mass using a balance. Yep. Part fill a measuring cylinder with water and measure initial volume. Place rock and measure final volume. Volume of rock. Yes. So we've got that, but not part filling measuring cylinder. But you get it. Define the volume, and then use mass and volume to calculate density. Mass divided by volume. Excellent. Got all the marks from that. I was a bit worried about that one, but that was good. Right. All this, the last question was pretty standard. Well, last rest was, 2.6, 2.5. Yep. 2.65, 2.45. And then we said it had to be chalk or flint, just because that's how the density is worked out. Chalk or flint. Yep. The student only took one set of measurements. Okay, yeah. So what is a mean can be calculated. Yeah, take the mean, which reduces the effect of random errors. Yes, the effect of small errors. Yeah, cool. I suppose I should say random, but that's what I meant by small errors, is the random errors, as opposed to like more systematic errors, like problems with your setup or whatever. What equation links current, potential difference in power? So I said it was P equals VI, which is correct. 11.2. Yeah, this again was just putting numbers into an equation, so that should all work out fine. I equals 4.4 over 40, and then 0.11 amps. And that as well. Yeah, but the rearranging is shown as well. I suppose that's the thing. Make sure you rearrange properly. Either with the numbers in or with the numbers out, or without the numbers, it shouldn't make a difference. Useful power output over total power input. That should be correct, yes, because that's in the equation sheet. Power LEDs and pavement, blah blah blah. So that was 3.4 watts. So yeah, so that's the rearranging bit there, and then it's 4 times 0.85, and then 3.4 watts. Excellent. So we got 98 then, I guess. Oh no, 97. So we lost 2 there, and then we lost 1 there. So 97% for the first one. 97%. Not bad. Could do with improvement. Oh well. Generally pleased with how that went. I don't feel like there was much that it was. Yeah, Transformers. I mean, I've not even thought about like real Transformers probably since I was 16. And then yes, it was just making sure in these longer text answers that I actually, say more things. I guess say be more explicit. Like actually say the efficiency, how the efficiency changes, not just that the efficiency changes. Like yeah, but there we go. Fair enough. I'll just open a new whiteboard. But not too bad overall. I'll take 97%. Kind of wish it was 100. Feel like it should have been, but oh well. We still had 6 minutes left at the end. Now it's foundation, and now we've got the higher tier one. Oh, and I'm gonna have the rest of my very cold tea. Which I made over 2 hours ago now. But there we go. Okay. Oh, oof. Yeah. Oof indeed. So. Okay, higher tier paper 1, all the same instructions, use black ink. In all the calculations show maximum marks 100. Right. Cool. And this is higher tier, so it'd be interesting to see. So we still have the same insert. It's just we have harder questions now. So with our knowledge gained from foundation 1, we'll just have to see how we do. Let's open a bunch of boards as well. There we go. Right. Pencils at the ready. 3, 2, 1. Let's go. Right. Okay, the same picture of the wind farm. Right. Oh, okay, well, we're starting off with the same one as before. I didn't think about that some of the questions might be the exact same, because you don't normally do both. Okay, fine. Well, alright, 696 million. Million, there we go. Over 580,000. Yeah, I mean, we've done that one already, so it's whatever that was again. 1,200 watts. Yep, no problems. Right, don't need to explain that, we've already done that. Moving on. 1.2. Not able to meet demand, we've done that as well. So I'm just going to put C last. Okay, I guess maybe I should just ignore the ones that we've already done. See last paper. There we go. We already got full marks on that one, so I'm not concerned. Okay, yeah, oiling. These are all the same. Yeah, these are all the same. Those both the same free text questions as before. So 1.3, 1.4. Oh, I didn't think the higher paper would... It's interesting that the higher paper starts with one of the last questions on the foundation. That tells you what they expect from you. Right, and then question 2 is also the same. Okay, right. Well, 2.1 we've done. 2.2, yes, this is all exactly the same question. You've got the making sure you plus minus correctly, so 2.2 is okay. 2.3 we did. 2.4 we did. Yeah, that's just errors. So I'm not going to bother with those. We've got the engineering one as well. Okay, so question 3 is all the numbers the same as well. So not going to bother with any of that. Okay, so it isn't as proper then, because we're not going through each question fully. Again, what's the resolution of the number to be? Give. Oh, okay, that's slightly different. 4.3 is slightly different. You actually have to say why it's more likely to be misread. Okay. And that was A is more likely to be misread because it just say because it's an analog thermometer. No. Because of the, what's it, gradation, I think it's called, gradation, as in the, like, where all the lines are, near impossible to tell if, oh, this is actually 87 as well, 87.4 or 87.5. Possible to tell if 87.5 or 87.5, for example. Resolution is lower. I think resolution is lower, is what it's looking for there. Yes, the resolution is 0. Oh, also, this is a free text answer as opposed to picking one from a box. It's not multiple choice, so but the resolution is 0.1, as we said in the previous paper. That's the point. I actually just realised 4.1 is also different, so let's go back to that. So it's put the method, right. Okay. I'll take it a bit more seriously now. Identify the independent variable, the dependent variable in this investigation. So, what is, if I can spell independent, I would hope dependent. So, we wrap the intake material around the can, we put a fixed volume of boiling water in the can, place the lid on top and measure the time taken for the temperature to decrease by a fixed amount. And then you repeat with the same thickness of different materials. So the dependent is the time taken. Yes, because that's what we're measuring. It depends on how insulating the material is. Our independent variable is the thing that we're changing each time that we have control over. So those are the different materials. So using different materials, which is independent, which we're putting around, then dependent variables, how much time it then takes to cool, to decrease by 10 degrees or whatever. So that all makes sense. Right, so we did 4.3. 4.4 then. For one type of insulating material, the temperature of the water decreased from 85 to 65. The energy transferred was 10.5 kilojoules. The specific heat capacity was that. Calculate the mass of the water in the can. Okay, so we've got specific heat capacity, we've got energy transferred from the water. So if we go to change in thermal energy, so this is the equation we would need to use, equals mc delta theta. So I'll put the number, rather than rearrange the equation as I did earlier, I'll put the numbers in first. So first of all, delta theta is 85 minus 65, which is 20. The energy transfer, 10.5 kilojoules is 10,500 joules, because that's kilo means 1,000, so 10,500 joules, which is 10,500 joules, and that's just making sure our units are all in the correct in the correct units. So we've got 10,500 equals m times 4,200 times 20. So M equals 10,500 divided by 4,200 times 20. It looks horrible, but you get it. Divided by 4,200, and then you just divide that by 20 again. There's a couple of ways you could do that with a calculator, but 0.125 kilos. Making sure that, there we go. Right, yes, it can be seen. Good. So yeah, so because we did everything in standard units, our answer is in kilos. If we had left it in kilojoules, it would have been in megagrams, which isn't very useful. So that was why it's good to make sure everything is in the right units. 4.5. Table 2 shows results for 2 different materials. So one of them took a lot longer than the other to decrease by the same amount of temperature. Explain how the results in table 2 can be used to compare the thermal conductivity. Ooh, okay. Are we using a higher tier only one here? No, that's all about coils and stuff. So we're talking about thermal conductivity. Okay, so not actually give us an equation for thermal conductivity. I guess not. Someone just for a change of state. No, okay. So, well, thermal conductivity, the higher it is, the more thermally conductive it is. So, presumably, I haven't done anything on thermal conductivity in a long time. But if something has a higher thermal conductivity, implying that it conducts heat better, that seems to make sense to me. So if it conducts heat better, it insulates worse, which means that if it's a bad insulator, it will lose heat quicker. So material X, it lost the heat much quicker. It lost that same amount of heat in 450 seconds, whereas in Y it was still quite hot until 745, where it lost the 20 degrees. So you would say that because time taken for Y is greater, thermal conductivity must be lower as what did I say earlier? The heat better insulators have lower conductivity, meaning my brain is getting frazzled now. Better insulators have lower conductivity, which means that it takes longer for the same mass of hot water to decrease by a set amount. By a set amount. Sure. That's something. Is that worth 2 marks? Maybe. How else could you talk about it? I suppose you would just say as a probably self-break would take one. Yeah, well, I mean, these first few questions have been very easy. I did think the marking was more for break than I thought it was. There's still 2 more papers I need to do after this as well, and it's already 4:30, so I'm kind of thinking I might have to do them in a second stream after dinner, because I do need to sort that out at some point as well. So probably won't move on to those papers before I end the stream for now, but there we go. 5.1. I will thank you for checking on with me there, Galantis. It's because I do just get I enjoy physics. It's almost like my pastime. So it's it seems very weird to just do exams as like a thing, but you know, it's what nerds are like, I suppose. The rod became negatively charged. Right. So okay. We've got the same setup as we had in the foundation, but we've got a different stuff we have to do. So this is just talking. So in foundation, you would talk through this, whereas in higher tier, you actually have to talk about it more explicitly. knowledge. So, well, remember from foundation paper that electrons are transferred from the cloth to the rod. Electrons have negative charge, therefore the cloth becomes positively charged. The cloth loses negative charge, meaning it gains positive charge. I suppose that seems fine. Figure 6 shows the negatively charged rod on a balance. Figure 7 shows another charged rod being held stationary above the rod. The rods do not touch each other, but you see the mass goes up. Wow, we've created mass. Why the reading on the balance increases, yes. So here's a secret. Balances actually don't measure mass. I know. Balances they give you a mass number, but they actually work by calculating the normal force of whatever is on them, which isn't actually much higher level than what I would expect, but yeah, that's how the balance calculates it. First of all, say electrostatic force acts on the rod by the other rod as they have the same charge, and like charges repel, as we said earlier. So the rod pushes into the balance harder. Newton's third law: every action has equal opposite action. Every action has equal and opposite reaction. Therefore, means the normal force increases, so the balance reading increases. And if that isn't worth 3 marks, I don't know what is, frankly. But that's it, yes. So because the rod is pushing it into, when you have scales, if you've ever tried to weigh your hand or your arm, if you push down on it, the reading goes up. That's not because your arm has increased in weight, it's because you're pushing on it. So, and that's why, it's because balances work like that. The balance had a zero error. Balance had a zero error. The zero error is not important in this experiment. Give the reason why. It gets cancelled out, essentially. Because we're interested in the change of mass, weight, I suppose. So the zero error gets cancelled out, I guess. Because if you don't know what zero error is, that means that if we take the rod off, the balance wouldn't say 0, it might say 0.5. But in this case, it doesn't matter if it's actually 100.75 and then 100.85, because it still went up by 0.1. That's the point. It may also be called a calibration error if you're in those sort of circles. So 5.4. A negative charge rod is held near an earthed conductor. Explain why a spark jumps between the negatively charged rod and the earthed conductor. Well, it'd have to be either very charged or very close for an actual spark to come out, but things like to be neutral is kind of one of the answers. So the electron, I suppose you could say that it induces a positive charge. because that's sort of how lightning works, is you have all these negative charges in the clouds. It induces a positive charge on the surface of the Earth, and that's why electrons flow. That's why we get lightning. So that's the same thing. It's just a spark as opposed to lightning. So I guess the points are the rod induces a positive charge in the conductor. So electrostatic attraction between the rod and conductor occurs. So electrons flow from the rod in the air to the conductor. That is a spark. That makes sense. Something along those lines. Maybe there's a point I've missed that it's trying to get at, but I feel like that's pretty much what we're going for. Right, 6.1. So again, we've got explain why it's used as opposed to fill in these sentences with words. It's that's walking you through what the answer to this question is. So we know the answer because we've done the other paper, but anyway. So transformer X increases potential difference and decreases current. The decreased current reduces the amount of energy dissipated by the wire to the surroundings. So increasing efficiency, I suppose. Increasing efficiency. Then, right, it's only talk about Transformer X, so don't talk about Transformer Y. So Transformer increased potential if it decreased current. The decreased current reduces the amount of energy dissipated by our surroundings in the transmission cables. Increasing efficiency. Yeah. I mean, it basically increasing efficiency is the answer, but yeah, I think you need to say explicitly what it does and why that works. So that might be worth 4 marks. I feel like there's more to say, but I'm not really sure what it's going for. So why Transformer Y? Well, let's see. Transformer Y. I suppose you get points saying what they do. Transformer Y decreases PD and increases current. I mean, you don't want like thousands of volts in your home. I suppose you could also say most appliances work off of a lower PD. So no need for a high potential difference. It's so annoying to say potential difference all the time. I would always type PD. But I guess it might just be more of an energy thing. In fact, is there anything about energy? There were a few things about conductors. No, I guess not. I thought I saw a few things, but well, there's all these energy things here, I suppose. I mean, if we're yeah, the power should still be the same. Yeah, I don't know. No need for IPD. I feel a bit weak. I guess just the overall effect is what's the overall effect? You can just have one power station from many. Well, it's not really transformable. I don't know. I'm going to leave with that for now. Maybe I'll come back to that. because we're definitely going to get, I mean, we've only been doing this one for 20 minutes, and we're on question 6 of 11, so we'll have time to come back and maybe I'll have thought of something. Back into Hornsdale in Australia. One day, the battery transferred 3.24 times 10 to the 11 joules of energy to the town. Potential difference of the power supply is that 230. Calculate the charge flow. Ooh, okay. So you got charge flow, but you've got joules and volts instead. Interesting. So we want the charge flow, which is current times the time, and this is in 1 day. So that is our time. So T equals 1 day, which obviously will convert into seconds later. So we need to find out what I is. So I is but we know how much energy was transferred, and we know what voltage was transferred. So if we have something with energy and I and V, then we'll be there. So we know that the power is the voltage times the current, and we also know that the energy transferred is the power times the time. So that is the same as the energy divided by the time for that. Okay. So we're trying to find I. So that means then that I is equal to EV over T. But then our final answer, we're going to be multiplying this by T anyway, so we don't actually need the T? Really? I suppose, yeah. Fair enough. So Q equals that times by T, which is just EV. So that's all we need to do. We just need to multiply those two numbers. It's just the energy and then the voltage. It's just that times that. So fair enough. But you must have marks showing how you got there. You can't just write down Q equals EV and then multiply the numbers and there you can just get the answer. That's not how that works. So 3.24. So it's that times 10 to the 11. So if we want it in 3 significant figures, we do 7.45 times 10 to the 13 coulombs, because that's how you measure. That's what you measure charge flow. So because that's times 10 to the 11, and then we're doing another 2, so it's two more orders of magnitude. So it's times 10 to the 13. Cool. Yeah, I feel like that's fine. So we didn't need to convert 1 day into seconds, which is nice. But it's 86,400 if you want to just know that for later. Okay, yeah, I mean, we've done this already, but again, last time it was multiple choice, 2 protons, 2 neutrons. Oh, here we go. We actually have to fill in the decay equation. A krypton nucleus decays into rubidium by emitting a base particle. Complete the nuclear equation. Oh yeah, right. So here we go. We've got your proton number and then your nucleon number. I think it's called something like that. Mass number, maybe. I'm not sure. Anyway, these are basically their own equations. So because that is essentially 85 plus 0. So we know that it must be 85 at the top. I'll just put in the symbols there. And then again, this is some number minus 1 equals that. So that's got to be 37. Oh, I didn't write it low down there. 37 rubidium. Okay, that makes sense. Yeah, cool. Yes. Yeah, that should be fine. Pretty sure. I mean, that's why you've got plus 1 there, right? Minus 1 there, right? Because it's like charge almost. The proton number of a proton would be plus 1. So the proton number of something with negative charge would have to be minus 1. 7.3. Now, this is a big one. Internal contamination of the human body means radioactive material is inside the human body. Explain how the risk from internal contamination is different to the risk from external by alpha. Right, okay. So, yes, alpha radiation inside the body, really dangerous. Outside the body, really not that dangerous. So, I suppose you have to say, alpha radiation can only penetrate 5 centimeters of air. So outside the body, alpha radiation cannot interact with anything past the skin. Anything past skin. So just keep that in that. Presumably, if paper stops it, a layer of skin should be enough to stop alpha particles doing anything. So inside the body, however, it's the source is able to reach vital organs. Essentially, thanks for following. Inside the body, it's also able to reach vital organs, so you then and it's very highly ionizing. And as alpha is highly ionizing, hopefully I can spell ionizing correctly. It's highly ionizing. There is a greater risk of damage. I mean cancer, for example, by the source. That worth 5 marks. What else could you say? Source is able to reach the radiation rather than the source. Radiation is able to reach, and has. You've got alpha is highly ionizing, which must be 1 mark. Can only penetrate a few centimeters of air, so it can't get past the skin. But inside it can reach organs, and so you've got a greater risk of damage. Sure, that makes sense to me. Back to this one. Okay. 7 point. Not 7. God. I do need to have a break at some point. Well, but it is 4:45, so. Okay, I've got the method used. What measuring instrument should be used to measure the volume of the water? Measuring cylinder, I guess. I mean, could use a few things, but presumably it's looking for measuring cylinder. Because you want 50 centimeters cubed, and a measuring cylinder gives it to you in gives you that sort of number. Those units anyway. Volume units rather than mass or whatever. Amazing radio. Yeah, well with yeah. It is funny, yeah. Well yeah, because that's beta radiation, I believe. So it's I didn't know about that though. You're not allowed to sit in that person's lap. That's quite interesting. Is it beta radiation? I actually don't know. You'd think it would be gamma, I guess, but maybe it is. Anyway, yeah, we've got multiple choice for like the first time this paper. What is a hazard in the student's investigation? Well, we've got very hot water, so. Right, so what is a hazard? Safety goggles are not a hazard. They are a method of mitigating risk. Heat-proof gloves, similarly, not a hazard. So it's either burns or boiling water. Well, the burns is the risk, right? Whereas the actual hazard is, I believe, the source of risk. So I would say the boiling water is the hazard. And the burn is what you're risking. So, yes, boiling water, I would say. That makes sense to me. 8.3. The initial mass was 0.08, final mass 0.071. The energy transferred was 25,200. Right. Calculate the specific latent heat of vaporization of water given by the student's data. Give the unit. Fine. So we've got the physics equation sheet here. Where do we have to go? We need the specific latent heat. I basically had a grilled cheese for lunch. It's more of a cheese bagel, but this stuff isn't that bad. And there's paper 2, which I think is meant to be harder as well. But you have to do both paper 1 and paper 2, whereas these are both paper 1s of different levels. So, so this is what we want. E equals ml. So, what is our m? Our m is actually a delta m. So, our m is 0.080 minus 0.0771, which is 0.009 kilos. I keep right-clicking by accident. We know our energy is 25,200 joules. So 25,200 equals 0.009 L. So L equals 25,200 over 0.009. And that I'm pretty sure we did as well before. Do I have it? Yeah, there it is. 2.8 million. Yeah. 2800000. And that is in joules per kilogram. Units are important. Yes, it actually has a specific one for units there. So that's one answer. That's one mark. That's one mark. That'll be a mark. That'll be a mark. And then something over there will be a mark as well. I think that'll be a mark as well. So I'm very happy with that. 8.4. Some thermal energy was transferred to the surroundings while the water was being heated. Explain how this affects the student's value. Ooh, okay. Well, so this energy is how much was supplied, correct? The energy transferred by the immersion heater, yes. Okay. So if some energy being transferred to surroundings means that not all supplied energy was used for vaporization, which means that so not all supplied energy is used for vaporization, which means that your specific heat is going to be too high, basically. So students' value will be higher than the actual value. Have I really explained that by saying not all supplied energy is used for vaporization? Explain how this affected the student's value. I mean, it'll definitely be higher than the actual value. It's just how do I properly explain? This is just me failing at English rather than failing at physics. I'm just trying to think of how to explain it properly. At least we've got nice lo-fi beats in the background. Yeah, I feel like... Yeah, so... yeah, okay. So number used for E in the equation will be higher than the true value. So student's value will be higher than the actual value. Yeah, I think it's just saying the number you put in the equation will be too high. So yeah, I think that's fine. Some of the water evaporated before it reached 100 degrees Celsius. Yeah, that's a thing. Explain how this affected the student's value for the specific... Right, so that means the... Some of the water evaporated before its temperature reached 100 Celsius. how will that affect latent heat vaporization? That's interesting. We didn't. Yeah, we've got the initial mass, then we've got the final mass. When do we actually measure the mass of the beaker water? Use the heater, keep it boiling for 600 seconds. Oh, okay. So when do you start doing that time? So you start it, so because it boils before it reaches 100 degrees, we've started this 600 second timer too early. So we started 600 second timer too early, assuming the student started the timer as soon as it started boiling. Or is it saying, or is that what it means? That it, I'm not sure what it's trying to get at, actually. Is it trying to say that we were boiling it for too long? No, that would just change the energy. I'm actually not sure what to go for here. This is interesting. This is something a lot of the stuff I falter on is stuff I've never not bothered with for a long time. Some of the water evaporated before its temperature reached 100 degrees. Yes, so that's what happens. Explain how this affected the specific latent heat. Specific latent heat. What does it really measure? It's how much. It's how much energy you need to put in for each kilo to boil it. But then if it's boiling too early, so the lower it boils, the less energy you need to put in. Water That's kind of gay. This is the first thing it's stumping me for more than 10 seconds. Explain how this affected the student's value. Rated before its temperature reached 100 degrees Celsius. Explain how this affects the student's value. Let's go back to the method. Determine specifically show some equipment use. Measure the mass of the beaker and the water. Use a heater to boil the water, keep it boiling for 600 seconds, and then measure the mass of the beaker and water after 600 seconds. So I think it means that some of it evaporated before it started to boil, which means that your mass will be lower than it would otherwise be. As in, too much evaporated. Yes, I think that, yes, okay. So, too much water evaporated, meaning the mass will be, the mass will be lower than if done without this factor. i.e. if none of the water evaporated until it reached 100 degrees, the mass would be higher up. It hath returned. Oh, it's like, fair enough. Liver pate. You can keep our cucumber to yourself. I'm not a fan of cucumber. Liver pate is an interesting choice, certainly. And rye bread, are you Finnish by any chance? I know that they love their rye bread. I'm not too big on rye bread myself, but it's not too bad. Typical Danish. I see. Fair enough then. I've not been to... I've been to the Netherlands very briefly, but it was just Amsterdam. It wasn't... it was only for 2 days as well. I did some interrailing way back when, but I've not been for a very long time. It was nice. I would like to go again. I would like to do more travelling in general, but there we go. Too much water evaporated, meaning the mass would be lower than if done without this factor. So the mass, so M will be 2 too high, meaning student's value will be lower. Oh, husband's Dutch sub. Oh, very nice. Oh, that's very nice. Brilliant snacks. Oh, really? What kind of snacks? I'm really big on British chocolate. That's kind of my fault. So when you say brilliant snacks, I'm kind of like, but British chocolate's so good. Student's value will be lower. It'll be lower due to this. Savoury snacks, right? Yeah. Oh, okay. Fair enough. Not too bad. What's your go-to savoury snack then, over in the Netherlands? Just so I know for the future. I'm more of a, I suppose I kind of go for crisps if I'm in the UK. That's kind of the only real savoury snacks I go for. Frickendell Special. Okay. I probably pronounced that horrendously, so I apologise for that. Okay, sure. Fair enough. Well, yeah, it's kind of a Germanic thing, isn't it? Having sausage as a snack and things like that, so makes sense. Okay, we've got a girl running upstairs and determining her power output. Fair enough. That's something to do in your spare time, I guess. The mass was 60 kilos. Oh, it's a shame. It's a shame she died, you know. The mass was 60 kilos. It's not anymore. She's dead. Height of the stairs was 175. Ah, there you go. You put a trick in the units there now. So let's just get that out of the way now. So height is 175 centimeters, which equals 1.75 meters. Because that'll be a mark. I can just tell without even reading the question. Well, it's more like, I'm bored. Let me calculate my own power output. I'm just going to run up these stairs for the next 1.4 seconds. Calculate the power output of the girl. Okay, so what we need to do here, we need to calculate her change in gravitational potential energy, and then we divide that by time to get the work done. So the work is, the power, I should say. The power is the energy over time, of course. Try it with anything else breathe through. Very true. Yes. Smoking is certainly not great. How was that? So, and then we need to do gravitational potential energy, which is, so I'll just say GPE. We used to write GPE, but here they actually do subscripts. So that's quite nice actually, because GPE was always annoying for me. I didn't like it. So we've got our height, and we've got our mass, and we've got G, and then that GPE here is the energy you'll put into there. So we can just write mgh over t, I suppose. The marking scheme won't like that. It'll want me to put numbers in everywhere, but hey-ho. So 60 kilos times 9.8. Oh, that's a horrible 9, but there we go. 1.75 meters. All that divided by the time, which is 1.4. And the power is... we have to get the calculator out for that, because I'm not going to do that in my head. That's not going to happen. So 60 times 9.8 times 1.75. And divide that by 1.4 to get 735 watts. Wow, that's like... What is it, horsepower in watts? I think a horsepower is like a few hundred. That's like a few horsepower. So, it's not bad. Didn't we do... I remember something in school where we measured how fast we each walk, and that was for something like kinetic energy or horsepower or something like that. And I think some people, the kids, it was like, oh, that's like 0.8 horsepower or something. I was like, alright, I don't know what that is at all, but fine. I wasn't as into cars back then, so but it's fun. You just say like, is your entire classroom like a Mini Cooper or something in terms of horsepower? So actually fun. Yeah, actually calculating horsepower is an interesting concept, certainly. The total power output of the girl was greater than the answer. Okay. That's... I guess you could talk about air resistance, but probably not. Probably not what it's going for. Interesting. So let's actually line it a bit properly. The total power output of the girl was greater than the answer. I'll check computers though. Sure, go ahead. The total power output of the girl was greater than the answer. Well, it must mean the energy was different, right? I like she's not even at the top yet. But there we go. I need to top some stairs. Why would it be greater? I mean, is it really like... Are we really talking about air resistance? Oh god. Air resistance and friction. Are we really talking about that right now? That seems wrong. Like, I can't believe it would be anything, any sort of relevant numbers, but I mean, technically, air resistance, friction, yeah, so some energy into surroundings, and then friction, some energy into the ground. I mean, that's technically two reasons. It feels wrong, but I'm not really sure what else it'd be going for. It's what else could it be going for? Total power output was different. Is it because it moved? No, because that's not work. Oh, that would just be going up. Actually, yeah, would it? Because you needed energy to move left, right as well. Okay. Needed to put in energy to move left, right, as well as up. Move left, right, as well as up. I guess. Yeah, surely. Because Newton meters, right? Force, and you've got your distance across as well as your distance up. The stairs don't go directly up. You do have to go across. So, yeah, there's some amount of energy you have to put that. Okay, that's like that's a proper, an actual amount. And then I guess there's friction. So, some energy went into the ground instead of just being used for movement. So, sure, we'll go with that, I guess. 9.3. Okay, we got a ticker box. Yay! The easier ones. The ones that don't require me to think about how to word things in English. A boy took more than 1.4 seconds to run up the same stairs. The power output was the same as the power output of the girl. What conclusion can be made about the boy's mass? Well, that's rude. So, a boy took longer than 1.4 seconds, which means that, but the power was the same. So, power equals energy over time. So, the power is the same. That's the same. And that's related to mass. Right, so that's proportional to mass, the energy. So, if the time goes up, that would normally make the power go down, but the power stayed the same. That's really a really bad symbol to put there, but fine. It's not a vector. Normally, if the time goes up, the power would go down, but it stayed the same. So that must mean the energy was also higher, which means the mass is higher. So the boy's mass must be greater than the girl's mass. There's no chance the boy's mass is the same, because otherwise, though, that wouldn't work out. Yeah, So in order for that fraction to still give the same number, the energy has to go up, which means the mass has to go up in this case, because the energy is proportional to the mass. So it's greater. Yeah, it's got to be. Okay, feeling more confident now I've written it out like that. 10.1. That's brilliant. I want an airplane like that. That's brilliant. Just ping. Can you imagine? Imagine having that in school. No work would ever get done. You'd just be tossing airplanes like that at everyone. Figure 11 shows a student launching a toy aeroplane. To launch the aeroplane, she pulls out, stretches the string, and then releases it. Sure. And this is 6 marks. Wow. Just before the toy aeroplane is released, the string has an extension of 0.12 meters. So E equals 0.12 meters. The mass of the aeroplane is 0.02 kilograms. And the spring constant, which is K, sure. K is 50 newtons per meter. Alright. Calculate the maximum speed of the toy aeroplane just after its launch. So when it says just after, that means don't think about air resistance or anything. So that's the moment where all of your elastic energy is all converted into kinetic energy. So what we need then is we need to find our elastic potential energy, which I'll label EPE, which is a half KE squared, and that is going to equal our kinetic energy, which is a half mv squared, right? And we want to know what v is. That's what we want to know. So we may as well just equate those. So we just say a half KE squared equals a half mv squared, which means we can cancel out the half. Well, screw that. We know all these other numbers apart from v squared, so I'm just going to rearrange that into square root of KE squared divided by m. So the mark scheme prefers numbers, but later on in life you prefer just moving letters around. Just otherwise you forget what the number represents, whereas if you just have it like this, it just works out. So, but let's put the numbers in now, so we still get that mark for showing our working. So our K is 50. Then we've got 0.12 squared, and all that divided by 0.02, and then all of that is square rooted, which, take out a trusty how well can you use a calculator. 0.12 squared, that's an easier bit to put in first, times that by 50. Then we divide by 0.02, and then we square root that, and wow, we get exactly 6 meters per second. So again, you get a nice unit. It didn't tell you to do it to 3 significant figures, which means you're going to get a nice number. In this case, we got a whole number, so it's very confident that that's what the maximum speed is going to be. But again, make sure you put in the speed and you put the unit. So all good stuff there. 10.2. Complete the sentence. Okay, grab the text. As the aeroplane moves upwards through the air, there is a decrease in the blank energy of the aeroplane. So if it's going up in the air, its kinetic energy is going to be going down. So the word is kinetic. It'll be gaining gravitational energy, but you can't just gain energy without losing some other kind of energy. So you're losing kinetic energy. Right, 10.3. Give one factor which would increase the distance the toy aeroplane travels horizontally before hitting the ground. Okay, well I can think of one very simple one. Well, I mean, so it specifically says horizontally. So how about angle the angle the aeroplane is shot at. So, because obviously if you just shoot it directly up, it's not going anywhere sideways. Whereas if you do it, 45 degrees, it'll go from much further distance. So the angle is very, it's a very simple answer there. Very simple factor. What else could you use? I mean, I don't know. You can argue, a longer string or a stronger string, or a spring rather, a longer spring or a stronger spring. What else you could do? You could decrease the mass of the aeroplane. Can make it less more aerodynamic, less aerodynamic. But I mean, the angle is just a very, very obvious one that you can choose, and it's much simpler to imagine. And now we've got some hair straighteners. They contain heating elements, and the picture is just some hair straighteners. There don't seem to be... I didn't realise hair straighteners have a dial on the inside of them. That's an interesting design feature. I suppose it's not near the heating elements, but I'd have thought you'd put them on the outside, but I've never used hair straighteners, so what would I know about them? When the hair straighteners reach normal operating temperature, an LED turns on. Draw a circuit symbol. Oh, okay. Oh, for an LED. Oh, right, okay. Well, we already know this then from the previous paper again. So it is that. I don't remember there being arrows when I learned symbols, but maybe there were. I thought an LED was just a diode with a circle in it, but there you go. I mean, it makes sense. 11.2. Figure 13, which is down there, shows the circuit diagram for the hair straighteners. Each resistor represents a heating element. The power output of the hair straighteners can be changed by closing different switches. Why do the hair straighteners not turn on when only the switch S2 is closed? Well, it's not a complete circuit. So it's very similar to the one we saw earlier. There are just some extra resistors, but you can see that if only S2 is closed, it's still not a complete circuit. So not a complete circuit, which means current cannot flow. That's the long and short of it. Is that there's no way of going from one end of the power supply to the other end unless S1 is closed, and so if only S2 is closed, you don't have a complete circuit, and that means you can't have your electrons flowing through your wire because they've got nowhere to go. They just kind of go like, I don't know where to go. 11.3. The hair straighteners have a maximum power output of 120 watts. The energy transfer to the hair straighteners to reach normal operating temperature is 3.6 kilojoules, right? We see a number that isn't in normal units, so let's go ahead and change that. 3.6 kilojoules, which equals 3,600 joules. There we go. That'll be one mark. Calculate the time taken for the hair straighteners to reach normal operating temperature when operating at maximum power. Okay, well, we've got P equals E divided by T. We know P, we know E, so we want to know what T is. We multiply both sides by T and then divide them by P. And we get T equals E over P, which you can also convince yourself just by looking at the units. You know that a watt is a joule per second. And so if you do a joule divided by a joule per second, you get 1 over per second, which is then seconds. So that's one way you can do that. So T with a very long tail is then 3,600 divided by 120, right? Yep, 120 watts, which is 30 seconds. There we go. Just about got that in without needing another board. It actually gives you the units, I guess. It wants to make sure you don't put in stupid units like minutes or years or something like that. You'd be surprised what some people think are good units. So, figure 14 shows the hair straightener circuit with S1 closed. Cool. Switch S2 and switch S3 are then closed at the same time. Explain what happens to the power output of the power supply. So the power output the power output should increase. I'm just interested by the fact that we've got 2 resistors in series for each one. That's interesting, to say the least. But I suppose, unless the resistors are really high, really large resistors. Oh, that's the last question. Okay. Ugh. So yeah, electric circuits. By and large, I'm okay with, but the whole series versus parallel thing, I generally, well, again, I'm generally alright. Explains what happens to the power output to the power supply. Yeah, so power output must increase. So power output increases. Increases. But you've got to explain why. So, what's the... I clicked on the wrong one there, somehow. There we go. Managed to... Oh, because it's not quite... Whatever. There was a thing, wasn't there, about energy, like power. So power equals voltage times current. Potential difference times current, sorry. It doesn't like you say voltage, when even though it's whatever. It's also current squared times resistance. So the current doesn't go down as much as resistance goes up, I guess. Well, PLA of V equals IR. Current is the same for all. I could have sworn on my thing there was a whole thing for adding resistance in series and adding parallel, because you add them as 1 over. Yeah, so because you've got so sorry, I'm thinking in my head, but if you have, for example, so there's your battery, and then you've got these resistors in parallel. So you've got R and R. The total resistance is equal to 1 over R. In fact, I'll call them 1 and R2. That total resistance is that, right? Whereas in series, so what I mean by that is, if you have them next to each other like this, and then the other side, so that's R1 and that's R2, then that total resistance is just them added together. That's the difference between series and parallel. So that's why parallel, your overall resistance is much, much lower than oh, sorry. That's 1 over R. I'm a physicist, you know. It's 1 over R equals that. Yes, I was thinking it shouldn't be that low. Yes. The point is the overall resistance is lower than if you just add them. It's not as easy to see, but that's how it is. So they have 2 resistors in each one, but I guess that doesn't matter for what we're doing, because you can just consider them. So because they're in series, you can just consider them as 1 resistor but with a bigger resistance. Does it actually say that all the resistors are the same? Because I don't think it did. Each resistor represents a heating element, right? Well, more heating elements are being used, so... Power output increases. Let me set that again. Right. So the power output increases. Power output of... Wait, does it? Well, surely it must do. Because so your resistance is increasing. Where was it again? Power equals current squared times resistance. So yes, you get more resistance, but then your current does go down, but I don't think it goes down as much as squared. So Your overall resistance has increased. Ugh. Yeah. God, I hope paper 2 goes better. Paper 1 is a bit rougher than I thought. Well, for the higher tier, the foundation one wasn't too bad. There were just a few points I missed. What happens to power output of the power supply? I mean, well, like, does it go up? But when it says power output of the power supply, the actual energy there in the batteries, that can't be going anywhere. That can't be, like, changing. But it's not an energy argument, it's an electrical argument of energy. So that's the question. It's explain what happens. So resistance in the circuit increases. The current would decrease because of this, because your potential difference is the same. Potential difference can't have changed. Yeah. Yes. Resistance in the circuit increases. Current decreases. But P equals I squared times R, as it says in there. So yeah, I think the power output must increase, right? Well, it does, because I'm sure that was in the foundation paper. Man, the power of electric circuits is getting me here. Current decreases, yeah. Yes. God, I just saw all 3s on my stream time. That was nice. God, I think I might just have to accept that I'm not getting all the marks for that one, because I'm genuinely not sure what it's looking for. This is why you revise, kids, because otherwise this happens. This is quite fun. This is really showing where my weakness is in the in basic physics, considering that I've been doing like very specific advanced physics for so long. It's quite fun going back to this foundational stuff and being like, oh yeah, I don't really know how that works. Electrical stuff's never been that intuitive to me. I know some people get it. I'm fine with some of it, and then some of it is just really I can't get over. Yeah. You know what? Life's too short, and it's 5:30. I'm just going to go ahead, mark these, mark this, because that was the last question and questions. So there we go. That was only an hour 10. Still spent over an hour on it, even though a lot of the questions were the same as in foundation. So let's see. So we started out, yeah, all this earlier stuff was exactly as in the foundation paper. So there's no reason to check all that. It should be exactly the same as it was. Yep. And similarly for question 2, yeah, that was just do all that, blah blah blah. And question 3 similarly. Apart from, yes, and then 4 was where it started to change. Right. Okay, question 4, let's change our colour to red. That's the traditional marking colour. 4.1. So we said independent were the different materials, independent is the time taken. Which is correct. Excellent. Okay, good start. You got the first 2 marks right. Good. 4.2 with the resolution 0.1 as we said in the foundation paper. A is more likely to be misread because the resolution's lower, essentially, I think is what it wants. Oh, really? Parallax. Okay, level of liquid maybe between lines. That's basically what I was saying, because, yeah, tell of 87.4, 87.5, right. Okay. Really talking about parallax error on a thermometer. Alright, fine. I mean, I guess, but... yeah, I mean... Yeah. Number of lines may be miscounted. I mean, true. That's a good point. Unlikely, but true. 4.4. So this is just doing an equation. Don't think there's anything worrying there. Yeah, 0.125. We've got 10,500 joules. Yep. And then overall that. Yes, well, yeah, yeah. All good there. Nothing wrong. 4.5 over here. Explain how the results can be used to compare the thermal conductivity of the two materials. Right. So, same temperature decrease in a shorter time means a higher thermal conductivity. Yep, I said the opposite, but you're allowed the converse. The rate of energy transfer is higher. Oh, that's what the second point is. It wanted energy transfer. Huh. Okay. I suppose it is energy transfer. Alright, -1. Fair enough. The student wrote, right, 5.1, explain why the cloth becomes positively charged. Electrons transferred from the cloth to the rod. Yep. Electrons are negatively charged. Yep. So there are more positive charges than negative charges on the cloth. Sure. Yeah. I mean, yes. I said the cloth loses negative charge, meaning it gains positive charge. There are more positive charges than negative charges on cloth. I mean, I'll be kind, give myself that. So here we are back to the rods on the balance. Now I wrote way too much here, so I really should get all these marks. There's an additional force on the balance, increasing the electrostatic force acts on the rod. Yes, there's an additional force because the rod is negatively charged, as they have the same charge. Yes, and charges like charges repel. Sure. As I did say, they have the same charge. Both rods have the same charge. And so the rod pushes. I said it out loud, but I didn't write it down about how they repel. But I did say, and like charges repel, as we said in the foundation. So I'm giving myself that. The balance had a 0 error. Only the change. Yes, change. Good. That was fine. I feel like I'm going to sneeze, but it's not. I don't know. Whatever. A negative charge rates here in Earth's conductor. So this would be interesting. I'm not sure if I really got what it was trying me to say here. Oh, you need a strong electric field or large potential difference. Right. Well, I did say electrons flow from in the air, so I just didn't say about breakdown of air. Yeah. Do not accept positively charged, even though you can induce a positive charge. Alright. Alright. I mean, alright. Fine. Fine. Alright. -1. Alright, I'll take it. Explain why transformer X is used in the national grid. Yeah, these... well, let's see. Increase potential difference. Good. Okay, this is what I thought. And decreases current. Good. Reducing energy transfer to surroundings. Yep. Increasing the efficiency. Yes. All 4 points. I'm very happy with that. I was worried. Decrease the potential difference to a safe value. Oh, safe. Right. That safety was the important thing. That makes sense. Okay. Well, I say voltage isn't what kills you, but current does, so. Anyway. Back to Hornsdale, Australia. So presumably we got this. This was fine. Whoa, what? What? I screwed up. How did I screw up? What's the saying here? Eh? Charge flow. So we got the energy, we got the voltage. What equation did you use here? Q equals E over V. Wait, what did I do? Hang on. What did I do? Eh? Right, let's go back to here. What did I do? Did I screw up? P equals IV, yeah. It doesn't even say where this comes from. It's you just starting off with that. How did that come from? How did that happen? I'm genuinely quite confused. Right, one day the battery transferred that much energy, right? Yeah. And P equals VI and equals energy over time. Yeah. So you've got VI equals E over T. So that means then that I equals... Oh, I'm such an idiot. I put the V there. I took the V and I put it there when I should have put it there. Wow. That was dumb. Yeah. That should be there. Which means that, yes, that should be E divided by V. Oh dear. Right. Oh, that was dumb. Oh dear. Wow. I think I'd be no marks then, but purely just because of that. That was so dumb. Wow. I can't believe I did that. That's what I do for. That's my fault for probably not taking a break, not taking proper time to actually rearrange my equations properly. I am genuinely quite disappointed in myself. Right, alpha particle, it's 2 protons, 2 neutrons. We knew that from the earlier paper. So that should be 85 and then 37. Yep. Excellent. 7.3. So the risk of internal contamination. Yep. So this is about alpha radiation and how dangerous it is. So we've got alpha radiation had low penetrating, can only penetrate 5 centimeters there. So externally stopped by skin, cannot go past skin. Internally it's absorbed by organs. Yes, I mean reach vital organs. As it's highly ionizing. Internal can then greater risk of damage, and I said cancer, but yes, you are allowed specifically cancer or mutations, which is also a thing. Fair enough. Question 8.1. Measuring cylinder. Yeah. You can also have burette or a beaker with graduations. Cool. What is a hazard? The hazard is boiling water, right? Yes, it is. Excellent. Good stuff. Right. This was the same number we got in Foundation, so I'm feeling confident with that. Yeah, 2.8 and joules per kilo. We've got change in mass is 0.009. We've got 25 to 100 equals that. And then L equals that. Yep, all good there. 8.4. Okay. Yeah, these ones I was a little concerned with. Less energy was transferred to the water. The student will be higher, yes. I mean, yes. I said that, but yeah. Not all was used for vaporization, so it wasn't transferred to water. It means the same thing, yeah. Some of the water evaporated. Right, this one. The measured change in mass is too high. the mass would be lower than if done without this factor. So m would be too high, so the value would be too low. Yes. Cool. Okay. Very happy I got those. Calculate the power output, 735 watts. Yep. Cool. So we've got height is 1.75, that's a mark in itself. Got that. I didn't actually write the energy was. But I mean, I wrote it all in one go, so I mean, it's fine. Yeah. Okay. What are the reasons then? Increases her kinetic energy. Some energy is wasted in muscle. Okay. Friction. Increases her kinetic energy. Okay. Fair enough. That's not really what I said. By saying left to right, I don't really mean... yeah, I should have just said kinetic energy. That was kind of dumb. Oh well. I should have thought that. Maximum speed. Oh wait, what? Did I miss one? Oh, here we go. Yeah, the boy. So his mass is greater, right? Yeah, boy's mass is greater. Good. 10.1. So we said 6 meters per second, which is correct. Nice. Here, the elastic energy. So I actually just calculated it all in one go. It's doing the forces was interesting. But yeah, I mean, we got there. But everything's there. So 10.2. Kinetic. Yes. Good. The angle. Surely that's like positive one. Increase the extension spring. More elastic potentially. Increase the angle. Yes. I mean, yeah, so you can increase the extension spring or more elastic potential energy, but like if you're angled up, it doesn't matter how much you do. So that's why I feel like angle is the best answer there. But fair enough. To the horizontal by a small amount. I mean, whatever, you know, the angle. Due to incorrect advanced information guides being issued for this question to avoid an issue because the question was discounted. Oh, well, hey, we got full marks to question 11 then. Wow, what happened? That's really interesting. I didn't realise that. Didn't realise that the one was discounted. Huh. Well, let's see how we do it anyway, because we got that. Not a complete circuit. So yes, needs to be close to complete circuit. Yeah. 30 seconds. Yeah, we've got 3,600 joules. We've got putting it into an equation and then the final answer. The total resistance decreases. Right. Really? It decreases. That's crazy. Fair enough. Okay. Huh. So I had that the other way around. Current. So yeah, I mean the current increasing makes a lot more sense with power increasing. It just confuses me, but you can add resistors to a thing and it decreases in resistance. It's a funny consequence of electric circuits. But there we go, I suppose. If you add them in parallel, I guess the whole thing decreases because of this form of parallel things. That's really strange. It's really strange. I don't like that. I just can't get that in my head, frankly. You just add resistors in parallel and it decreases the resistance. Anyway, so, well, we got full marks because everyone got full marks for 11 anyway, but we lost 1 mark there for not saying kinetic. We lost a mark here for not saying safety, about having a lower voltage. Did lose 4 marks there, but it was just an equation. It was literally just I forgot to put the V down there. That was dumb. So that's just a dumb mistake. It's not an actual knowledge mistake. We did lose a mark here because I didn't say about energy arguments, and otherwise we were fine. So again, that's 97%. Yes, you can argue, actually I lost 4 marks, but nah. I think having both 97%, that's a nice symmetry there. It doesn't matter how hard the paper is, it's still 97%. Okay, fair enough. That's that. Let's continue that, unpause that, and may begin the next paper now. So, foundation paper 2. So we had a very brief look. I didn't actually look at the content of any of the questions, but we just briefly looked at what would show up. So we've got some magnetism to start with. So complete table 1 to show if the magnets would attract or repel. So we've got some lovely bar magnets. Tick 1 box in each row. Cool. Well, let's just bring up a quick table there. That's lovely. We need to put tick in there after all. So attract or repel, we've got south to a north, so that is attract. North to a south, that is still attract. South to south and north to north, both those repel. So very similar to electric charge, like repels and opposites attract. So north being probably the positive end, and south is the negative end. You can think of it like that. Yep, and there we go. That's something I drew actually at one point in one of the last papers. So figure 1 shows the magnetic field around a bar magnet. Which statements are true for the magnetic field shown in figure 1? We have to tick 2 of these boxes. So the foundation paper, they typically lead you through the reasoning, or they kind of prompt you. Whereas in the higher tiers, if these questions are exactly the same, it will ask you, it might say what statements are true for the magnetic field, or give 2 statements that are true for the magnetic field, or give 2 facts, right? But it won't give you a multiple choice list like you do in the foundation papers. So that's most of the reason why they're easier. Even though it's covering more or less the same content, it's just you're being helped along a bit more, which is how it is. So the magnetic field gets weaker further from magnet. I mean, that's definitely true. We see here we've got magnetic field lines, and so there's also the knowledge I have from university, which is that it falls off as the distance from the magnet squared. So there's that. Magnetic field is strongest at the poles. I mean, that sounds true. Right. Okay, the magnetic field lines point from south to north. That isn't true. They go from north to south, so we can safely rule that one out. Magnetic field lines all meet at a single point? No. No. I mean, you can see that they don't. They're all on different points of the magnet, so I think we can safely ignore that one. And then the magnetic field is uniform away from the poles. I mean, it doesn't look like it's uniform anywhere. It's very uniform to me would be lots of straight parallel lines, right? And parallel lines. So I think, yes, the first 2 boxes seem correct to me. So we will tick those. Very good. Figure 2 includes an electromagnet. Okay. Oh yeah, okay. It's not just the electromagnet. Fine. That's really weird. I'm just drawing a circuit diagram, and then just one element is incredibly detailed. It seems weird, but sure. It's even got a couple of paper clips along the bottom. That's fun, I guess. 1.3, I'll just do a new one. We've got infinite whiteboards, why not just use them? Which metal is used to make the core of the electromagnet? Tick a box. So here we go. For electromagnets, you use iron. And the reason is there are only 3 metals that are magnetic in themselves. So you've got iron, cobalt, and nickel, I believe. So technically you use any of those 3, but in this case, iron is the only one of those 4 that is magnetic in itself. So it's iron, basically. And this is why iron is used in transformers and things as well. So it's that's what it is. I mean, there's not much to explain it. That's just how it works. Complete the sentence. Choose the answer from the box. The switch is closed. There is a current in the either coil, metal core, or paperclip. So the paperclip isn't part of the circuit, really, or not the basic circuit, so there shouldn't be any current in the paperclips. The metal core, that seems to connect the wires, so you'd think it's there. Which metal is used to make the core of the electromagnet? Yeah, and then you've got a coil, but... Oh wait, no, they are connected to the coil. Right, yes, it's the coil. It's cool because that is what you do. You wrap wire around a metal, so the current will be going through the wire. So the word is coil, and it's only one word, so I'll just do that. There's a current in the coil. Yes. Yeah, I mean, if you connected it to the core, I guess you would then have it through the core, but in this case, it is the coil. 1.5. The number of turns on the coil is increased. The current remains the same. How does this affect the strength of the magnetic field around the electromagnet? So you're increasing your electric field strength because you've got more turns in your coil. So you've got more wire around it, basically. So if you've got the same current, but you've increased the number of turns, then the magnetic field will be stronger. So you'll be inducing a magnetic field through the iron. Yes, that's the electric fields and magnetic fields are intrinsically linked, and that's part of it. Right, I've still got quite a lot of space here, so we'll put 1.6 over here, or 1.6 apparently. The metal core was removed. The current remains the same. How does this affect the strength of the magnetic field around the electromagnet? It would be a lot weaker. There's a reason there is iron there, and it's because why is it? Why? What's the actual reason why? It's a good question. So I can't think of it exactly. So iron has it's a concept called ferromagnetism, which obviously isn't something you talk about at this level. But anyway, yes, the magnetic field will be weaker. I mean, yes, you can just have coils, and as long as you've got electric field around it, you will then have a magnetic field through it, and it'll be turning like that, right? So that's the way it goes, depending on which way your current is. So what the iron does, the iron sort of focuses it, I suppose. Is that a good way to say it? I think so. Something like that. Anyway, if you remove the metal core, the magnetic field is weaker. So, okay, we've got some hailstones. Hailstones are small balls of ice. They form in clouds and fall to the ground, as opposed to falling into outer space. Show different sized hailstones. Which force causes hailstones to fall to the ground? Does air resistance make things fall down? No. Does gravity make things fall down? Does magnetic force make things fall down, or does tension make things fall down? It is gravitational force. That's what makes things fall down. So that's got a little space here as well for this little smiley guy. Yes, what force causes hailstone to fall ground? It's their weight, and the weight comes from gravitational force. Which in our little equation sheet here, we can see gravitational potential energy, right? MGH. So this is what leads to weight. Weight is just mg, right? Your mass times gravitational field strength. So that's the force that causes anything to fall to the ground. 2.2. Yep. As the hailstones begin to fall, they accelerate. Which force increases as the hailstones accelerate? Air resistance, gravitational force, magnetic force, or tension? Well, there's still no magnetism or tension involved. Which force increases? Well, the gravitational energy decreases as the height goes down. So I don't imagine the force increases. So air resistance, though, that is I remember in A levels, in our mechanics class, we actually modelled how air resistance relates to the speed of paper cup cases. So we would pick up, drop one, and then measure how fast it falls, and then stack two on top of each other, see 3, 4, and it was something like it's multiplied by speed to the power of 2.2 or something like that. That was the somewhere around there. So in fact, that's 2.2 is kind of a funny coincidence. After a short time, hailstones fall at terminal velocity. Which of the following statements is true at terminal velocity? So terminal velocity means that it ain't getting any faster. The hailstones begin to slow down. No. Terminal velocity, they stay at terminal velocity until they fall down. So they don't slow down, they stay the same speed. The mass of the hailstones increases? No. Why would its mass be increasing? That's a very strange thing to say. The only way its mass could be increasing if there was more matter going into them, but if anything, there would be matter falling off of it. The resultant force is 0. That is correct. So when your resultant force or net force is 0, you don't accelerate, right? That's F equals ma. So if where F is your resultant force or net force, I always wrote it as net force. Of course I didn't. Yeah, that looks like the word net. Anyway, so if your force is 0 and your mass isn't 0, then your acceleration must be 0, because that's the only way you could make that equation work. So yes, when your resultant force is 0, your acceleration is 0. That is true at terminal velocity. A scientist investigated how the terminal velocity of hailstones varies with their diameter. Okay, we've got terminal velocity on the y-axis and we've got diameter on the x-axis. Estimate the terminal velocity for a hailstone with a diameter of 80. Oh, okay. So we need to extend that. That looks like there's a slight curve. So, but I guess, well, I can't like draw lines or anything. Is there a curve? Yeah, it does look like there's some kind of curve. So if I had this paper in front of me, I'd have a ruler probably and just draw a vague line. But essentially, you just want to follow the line of best fit. And we've got 80 on the x-axis there. So somewhere around 43. Sure. So 43 meters per second. And I'll do an about. Approximately 43. Show how you attain your answer. I would have tried to sketch along the best fit line, basically. But I don't know. I guess I could. And then and that's 80, and that's 43. Sure, that works. Just erase that so I know it's all part of the same question. There we go. 2.5, assuming? Yes. Give one reason why a hailstone with a large diameter has a greater terminal velocity than a hailstone with a smaller diameter. So we've got power, pressure, temperature, and weight. Well, presumably hailstones all have roughly the same density. So I'd imagine if it has a large diameter, it means it has a larger volume, which means it must have a larger mass. If it has a larger mass, that must mean it has greater weight. So temperature has no effect on terminal velocity, as far as I'm aware. Pressure, similarly. It's a strange thing to say. And then power, there's no talk of energy here or anything over time, so power isn't very relevant. 2.6. After falling, the hailstone hits the ground. Good. Figure 5 shows the forces acting on the hailstone at the moment it hits the ground. Bam. What is the magnitude of the resultant force on the hailstone? Okay. Well, that's fairly simple. We've got 0.63, so what's the net force? The magnitude of the net force. So in this case, we've got 0.63 up and we've got 0.15 down. So that is 0.48. Yep. So 0.48 up. Right. Yeah, because you could, if you want to imagine direction, if that was up as well, you would add there, but because it's down, it's minus that amount up. So it's 0.48 up. But yes, the magnitude is 0.48. It wouldn't ever be 0.15 or 0.63, and then it's 0.78 if you don't realize that you're meant to minus those. Yes, force has a direction, which is why it says magnitude, as opposed to what is the resultant force, because you would have to give a direction as well. It doesn't make sense to talk about force without saying a direction, basically. What is the direction? Right, up. Up. There we go. I argued it there, but... Cool. 3.1, and we're into space. The sun is at the center of our solar system. What type of object is the sun? The sun is a sun, as some people would say, but no, it is a star. Star is the general term for things like the sun. So that's a nice easy one. 3.2. Well, the space, may as well use it. What is the name of the galaxy our solar system is part of? It is called the Milky Way. So it is number 2. Andromeda is a galaxy. Sombrero and Tadpole, they are all galaxies. But yes, the Milky Way is the galaxy that we're in. And that isn't any kind of theory. That's just what it is. There's also, that's just a memory test. There are a lot of questions in physics. There are a fair amount of questions in physics that are just memory tests. There are things you just have to know. But generally, because you know those things, you can then infer or figure out a lot of other things. Table 2 gives information about some of the moons in our solar system. Okay, we've got Ganymede, Titan, Europa, Charon, and then their radius in kilometers. What is a moon? That's certainly a question. What is a moon? It is a planetary body that orbits, or it is a body that orbits a planet, I suppose. It is a celestial body. There we go. I don't think I'm going to get a specific mark just for saying celestial body, but that's more accurate to what it is. Yeah. Let's say with regular periodicity, i.e., it's not like a captured comet or just a random asteroid. It has a regular period, and it orbits with regularity. That's my point. 3.4. This will be the last question I put in this little bit here, and try not to go past that. Okay, it looks like it's a text one anyway. So let's get that in. A student researched the radius of some planets in the solar system. The largest dwarf planet is 1200, the smallest planet is 24. Student made the following conclusions. Dwarf planets are always smaller than moons, and planets are always bigger than moons. Give one reason why each of the conclusions are wrong. Okay, fair enough. Research the radius of some planets in the solar system. Dwarf planets are always smaller than moons. Well, no. So the largest dwarf planet is 1190, and Charon up here is 606. So I suppose we could start off by saying Charon, a moon, is smaller than a dwarf planet. And then number 2, planets are always bigger than moons. The smallest planet is smaller than Ganymede. So, Ganymede, a moon, is larger than a planet. I mean, we could put in the numbers, but meh. Larger than, I guess we could just say the smallest. And the smallest planet than, and larger than the largest dwarf planet. Yeah, I don't see how else we could say anything about that. Makes sense to me. 3.5. The Earth's moon and the ISS both orbit the Earth. Give one other similarity and one difference between the orbit of the Earth's moon and the orbit of the ISS. Okay. Similarity. Oh no, my rate. Ooh. Okay, might be back now. That was strange. Okay, good. Right, I don't know what happened to my stream health there. It just sort of died. Good thing I was checking on it, I suppose. Let me just grab that back up. Right. Okay. Where were we? So, yes. Coil, yes. 1.5. I said the magnetic field be stronger, and that is correct. 1.6, magnetic field be weaker, which I said. The smiley face, to get a little mark for that. 2.1, I said gravitational force. Yep. And then 2.2, we said air resistance. It's yep. 2.3, resultant force is 0. Sounds about right. Yep. 2.4. Right, about 46. Alright, yeah. Line extrapolated to 80. That's the point. It even says allow a straight line, even though not necessarily, but fine. Yeah. If I had paper, it would be easier. 44 to 48. Yeah. Oh, God. Give one reason why Hellstone large diameter, so I said it has greater weight. And that is correct. Nice. 2.6 is 0.48 newtons. Yep, that's the right one. Because that'll be that one, yep. What's the direction of the resultant force? I said up. Up. Indeed. Ignore north. I mean, yeah, why would you say north? A star. It's a star, guys. Yeah, what is the sun? It's a star. We are in the Milky Way. Correct. Oh, a natural satellite. Right. That was what they were talking about. Well, I said celestial body. So, yeah. You can't, no matter what, you can't argue that any satellite we put up is a celestial body. So, I'm going with that. Charon is smaller than the largest dwarf planet. Yep. And Ganymede is larger than the smallest planet. Yes. Good. 3.5. Similarity. Circular orbit. Yep. And difference. Orbital height is what I said. Yep. 3.6. Why aren't there many people in the ISS? It's expensive. You can also say dangerous. Difficult to get to, few opportunities, or only trained astronauts is probably the best answer, really. Right, 4.1. Center of mass, I said, which is correct. 4.2 is directly proportional, which I definitely said. Yep. 4.3 is 0.22 kilos. Excellent. Obviously, the kilos was already provided there, so. Right. Next bullet. calculate the weight of one orange. So we said 2.156 newtons, correct. 4.5, 0.015 meters, which is correct. 4.6, 400, so that's right. 4.7 returns to the original length shape. Allowance returns to 3.5, yes. Good. And then into 5.1, ultraviolet visible light. So we said ultraviolet travels at the same speed, which it does. Good. D and then C, that's correct. 5.3, we've got 85, 35, 180, and then UVC. Good. Right. Okay, so here's indicative content. Ozone absorbs all UVC. Completely stopped by ozone layer. Yeah. Is the most dangerous. So I said, yeah, has the highest iron. Yeah. Almost completely stopped and medium risk. Yep. Does not absorb any. Least dangerous, lowest ionizing power. The greater the ionizing power, the greater the absorption by ozone. Yeah, sure. Greater the ionizing power, the greater the risk. Yes. The higher ionizing makes the highest risk. Yeah. Yeah, okay, cancer, sunburn, yes. I suppose I should have actually said what the risk is, but yes. I feel like my half-assed answer there is I'm excited to see what the answer to this question is. One piece of evidence that the ozone layer doesn't absorb visible light after being told the sun emits visible light. Our eyes detect visible light. I mean, yes, but it would be dark all the time. Or specific effect like particle growth. We can see the sun. Is that not good enough? We can see the sun. What do you mean? I guess that the reason for that is our eyes detect visible light. Fine, whatever. I was giving myself that mark because I deserve it. Transmitted, absorbed. Yep. So mark for each of those. 6.1. I said it could only be 100 kilometers, which is correct. And then it's gas as for what is most of the atmosphere. Yep. Because if it was soupy atmosphere, it wouldn't be like that. 90,000 pascals. Yep. 11,000. Yep. Good stuff. And then we've got 6.5. The density of the air decreases and the mass decreases, which are the two that I ticked. Very good. Use equation. So we should get 94,000 pascals, which we do. Excellent. And there's the working. And then question 7, wavelength frequency. Yep. And then parallel. And then 8,000 hertz. That should be correct. Yep. 0.000125 or 0.125 milliseconds, I guess. Yeah, sure. Doesn't actually say anything about milliseconds, but there you go. 330 over 6,600. Yep. 0.05. Yep. And then meters. Yep. Distance travels to speed times time. Allow any correct rearrangement. Yeah, good. As it should. So t equals 0.04. Yeah, because we got that, and that's what we wrote as well. Good. So loudspeaker B is further from technician. Oh, I didn't realize I actually had to say that. Right. Take more time to travel. Sure. So the sound arrives at the same time. Yeah. I think I went over a bit too much. I'm gonna do that. 8.1. Capacity of the battery. Yep. Speed, mass, weight, uphill, downhill, condition of the road. Efficiency of engine. That's basically what I said. So that's fine. Acceleration is delta V over t. Yep. Very good. 20 equals 28 over t. T equals 28 over 20. 1.4 seconds. 8.4 v squared minus 0 squared equals 2 times 10 times 605. 12,100 equals 110 meters per second. 8.5 work FW equals FS. 8.6 7,500 meters, 4,000 times 7,500, and then 30 million joules. 9.1, yeah. I described it. It's place a glass block on a piece of paper. Hey, that's draw around the glass block. Yeah, well, yeah, I said draw that line. So use array box, mark the array of light entering and emerging. Yeah, sure. I mean that's all fine, really. I actually said draw a protractor there, so. Yeah, all points plotted correctly. I mean, that's very simple. Curved line of best fit. Yeah, it is. That's the point. Make sure it's a curved line of best fit, not a straight line. Normal drawn at 90 degrees. Yep. And straight line drawn with a ruler. I would if I could, but I can't. 9.4. So protractor isn't in the way. Right, lasers diverge less. Surely that's... Ray in method A does not diverge. Yeah, it diverges less. Make it easier to judge the center. Yes, determine the angle of the middle of the light beam. Does not need to be repositioned. I thought the light would we end up going through the protractor. I guess that's not what it's going for. Which would affect it, right? Well. Alright, I'll be harsh and say I don't get those 2 marks then. Because that gives me 98%. Which, not bad. But yes, I suppose I should have thought. Yeah. I didn't even say that it would. I just thought it would give you. Oh, I don't know what they were doing with the different equipment. Yeah. I kind of thought the projector would just be in the way, but don't know. Doesn't say that. Don't have to mark the position to raise the light. Yeah. But everything else was, yeah, very simple. So happy with that. And there we go then. So we're going into our final paper, which is only 8 questions. Right, it's only the higher tier one. It's 8 questions. So we may be going through this quite quickly, depending on how similar these earlier questions are to the foundation, but we'll see, I suppose. So, getting ready then. 3, 2, 1. Start now. Right. Okay, we're starting with the supercar. Right. The battery car needs to be recharged. Okay, we've already done that. Okay, so 1.1 we're done. Yeah, you can make the more efficient motor, whether, how big the battery is, etc, etc. We've done 1.2. That was in the foundation. We did exactly that question with the same numbers in foundation. Did we do that one? I think we did, right? Yes, there it is. 110 meters per second. Done that one as well. That question is just exactly the same. Yeah, done 1.5. Traveling at maximum speed. Yeah, do that one as well. Okay, all of question 1 is done. Okay, I've got the same instance and refraction. Describe a method. Yeah, that's exactly what we did in last paper as well. It's the same table, so yeah, we've done that one too. I did say these first ones might be, and we've done 2.3. I'm at least checking them to make sure they're not different in some way. Yeah, 2.4 is exactly the same. Okay, right, speed limits, that's different. The braking distance of a car increases as the speed of the car increases. Give 2 other factors that increase the braking distance of the car. So that's straight from driving theory. How well do you remember your driving theory, if you've done your driving test? Give 2 other factors that increase the braking distance. So remember, it's the braking distance, not the thinking distance, specifically the braking distance. So we could say wet or icy roads as an example, because that increased. So from decreased friction. So you're not being able to put down enough friction, so you start braking and it takes longer to reach 0. What else would increase the braking distance? Well, going downhill, I suppose. Downhill. Going downhill, it would take longer because your weight's pulling you down more. So, yeah. Seems fine. 3.2. Explain why the driver's reaction time affects the thinking distance of the car. Well, Hey, Josky, how you doing? We're going through GCSE higher tier physics paper at the moment. So if you're not from the UK, this is a paper that 16-year-olds do. So we've been doing a bunch of papers today, which is what the timer is. I'm getting a bit tired of it, but this is the last one, so I'm powering through. We're doing pretty well. 97, and the last one was 98. So still getting, even though I've got a physics degree, still messing up a very, very small amount. But otherwise, just pretty nice chill time. If you just want to hang out, feel free. Probably be going for another hour and a half, something like that. Depends how stuck I get on the later questions, I guess. Or if I just feel like doing something else. I should say. Yes. Right. Explain why the reaction time affects thinking distance of the car. So we're doing straight up driving theory at the moment. I mean, the thinking distance is just the distance the car travels while the driver is reacting, right? So I kind of just want to put an equation down for that. Affects the thinking distance. Yeah. I mean, yeah. We will just say thinking distance is distance travelled before driver applies the brakes. So increases if reaction time increases. I feel like that's fair. So increases if reaction time increases. I feel like that's 2 points. It's 2 marks. It's pretty standard stuff. 3.3. So yeah, the thing is, because we're doing, typically you would only do paper 1 and paper 2 of either foundation or higher tier, but because we're doing both, there's a lot of overlap. So these 2 questions are exactly the same on both foundation and higher tier. So that's why you're not seeing the answers. I've just ticked them because I already covered them a little bit ago. So 3.3. Oh, here we go. We've got a big question. Scientists investigate how drinking alcohol affects a person's reaction time. Figure 5 shows the results. Sure, before drinking alcohol and after drinking alcohol. This is before having fun, after having fun. Oh, yeah, we've got fun on the x-axis, and we've got amount of people. Which of the following conclusions can be made? Tick 2 boxes. Okay, well, we don't have to write anything. We just have to tick some boxes. I don't really have space. I'm just going to start. I've got infinite whiteboards. Let's just use them. 3.3, especially if I'm drawing threes like that. Good God, I'm going to need more whiteboards. Right. Got 5 boxes there. So, every person's reaction time increases after drinking alcohol. That's not necessarily true. Perhaps someone up here just needs a small buzz going, and then their reaction time goes down. Like, that's entirely possible. So, it can't be that one. Mean reaction time increases. Yes. The mean reaction time must be somewhere around here, because that's the middle of this big lump. And the middle of the next lump is somewhere over here. So the mean time does increase. Absolutely. Some people's reaction time is not affected. You don't know that for sure. Yes, there's this overlap where perhaps there was someone around here who didn't move, but you're not seeing every point moving to every other point, so can't say for sure. The number 4, the change in reaction time is not the same for all people. Yes, that's definitely true, because the shape is different. If it was exactly the same for everyone, it would be the exact same shape, so we'll say that one. There's a smaller range of reaction times after drinking alcohol, just checking, but no, that goes from 0.3 to 1.3, so it's a range of about 1, whereas this range is only about 0.8. So the range actually increases. So if it was the other way around, then that would be true. But no, it is not true. 3.4, we got some average speed cameras. Yeah, it showed some speed cameras. The speed cameras determine the average speed of cars on the road. The speed limit is 20 meters per second. The cameras are 1.5 kilometers apart. Calculate the minimum time it takes to travel without breaking the speed limit. You can't just go whatever speed you like. Fine. So, and it says use the physics. So we've got this insert with a bunch of equations, but most of these are very simple to remember. I've referenced it a few times just to check, but it's that's fine. So we've got I didn't go back on pen. Right. So our speed is equal to our distance divided by time. Our speed is 20 meters per second. Our distance is 1,500 meters. I should just say at the start, 1.5 kilometers equals 1,500 meters. Typically, that is worth a mark, so it's well worth putting. And then our t is there. So rearrange that, 1,500 over 20. And that is 75 seconds. But we are allowed scientific calculator. We can just double check that maths hasn't broken in the last few seconds. There we go, 75 seconds. Good. That's the minimum time it takes to go there and not break the speed limit. The average speed of a car between the cameras and the average velocity of the car between the cameras are different. Okay, what's the difference between speed and velocity? So, speed is a scalar. I haven't put in the question number here. Speed is a scalar, but velocity is a magnitude. So velocity is magnitude. Velocity is a vector. There we go. Vector quantity. So vectors have direction, whereas speed is just a number. So if you're going 50 miles an hour, it's always 50 miles an hour. But that's your speed, but your velocity is 50 miles an hour in that direction, or it's 20 miles an hour in that direction. It's not. So that's the point. So because this road curves, that's not just a nice bit of the picture. The road does actually curve, so your velocity is changing. It's like how when you spin something, its velocity is changing, even though its speed is the same, because it keeps changing direction, but it's staying the same speed. Anyway, so that's the most important thing. So we say, basically our points are speed is scalar, velocity is vector, road curves, so the direction changes even if speed remains the same. Yeah, so I think that second sentence is basically 2 points. So I feel like that's worth 3 marks. Yeah. I think there's definitely a point for pointing out that one's a scalar, one's a vector. So that should be right. I'd be surprised if there's anything I missed there. Oh, we're already in question 4. And this is a very similar picture from the last paper as well. But okay, it's more of a free text. So we got the foundation paper had a similar question, but it had guidance with it. It was like a choose from some boxes. So why does the hailstone accelerate? I mean, gravity, basically. Wait, hold on. Sure thing, Josky. I mean, can you not just find a charger? Oh, thanks for following me. Hey. Do you not have a charger around at the moment, or are you out or something? Or weight pulls the hailstone down, basically. Weight pulls the hailstone down. Oh, well, I suppose we need to say resultant force, right? Weight is okay, let's be a bit more proper about this. Weight from gravity gives the hailstone a net force down. Net force down. I don't know why I capitalized force there. It's not the force. Goes net force down, so it accelerates. So it accelerates down. That's a bit too wordy for one mark, but I think that should be enough. Stops accelerating, reaches terminal velocity. Why does it reach terminal velocity? Aha, terminal velocity. Right, let's make a new whiteboard over here. So you have your hailstone here. This is its weight. And then up here, we've got air resistance, which I guess I'll put in an actual text thing. So that's friction, air resistance. Okay, I'm really comfortable. Okay. Fair enough. You know, why not? So, I mean, I've been there. I've been there, certainly. I've been there with not wanting to, when you're turning on one side and your charger cable doesn't quite reach your phone. Yeah, you can't. You don't want to turn over because you're too comfortable. I've been there. So the air resistance depends on speed of the hailstone. Nip. As speed increases, just air resistance increases, just to be very explicit about that. When magnitude of air resistance equals the weight, there is no longer a net force or resultant force. No net force means no acceleration. I was just bend the charge. Mine would snap. So after years of abuse, there's no acceleration. So speed remains the same. There. That's well worth 3 marks, especially with that picture. That's a beautiful picture. I want to hang that on my fridge. 4.3. And it's another multiple choice. Yay! We've got 3 boxes. A scientist investigated how the mass of hailstones affects their terminal velocity. Figure 8 shows the results. Why does the terminal velocity increase with mass? So we've got, as mass increases, the cross-sectional surface area of the hailstone increases. That's probably true, but that wouldn't necessarily increase the terminal velocity. If anything, that would decrease it, because that would mean you've got more air resistance. As mass increases, the volume increases, and as mass increases, the weight increases. Well, yes. It probably increases the volume. It definitely increases the weight. because weight is just mass times the gravitational field strength, and that's constant. So that is 9.8 brackets 1, somewhere around there. So if your mass goes up, your weight has to go up. And if that weight goes up, then that means the air resistance has to get even higher before you have what happens here, where they become equal. So that it's got to be the third one. But as mass increases, the weight increases, and that's why terminal velocity increases with mass, because this force is greater, so you need a faster velocity to get a better friction, more air resistance rather. 4.4. Let's just make sure I don't go into my little square there. Beautiful. Right. 4.4. Explain the difference in the maximum kinetic energy of a hailstone with a mass of 10 and a mass of 20. Okay, so I guess for that we just want to get what the... I don't need a text for that then. So when we've got 10 gram, we've got a terminal velocity of 4 meters per second. And then at 20, it's 32. So 10g, oh god, maybe I do need the text, 4 meters per second, and then 20g, it's 32 meters per second. So kinetic energy, which we do have on our sheet, but it is a half times the mass times the speed squared. So that's all that is. So as the, so the difference in kinetic energy, the difference in maximum kinetic energy will be you've got a factor of 2 from doubling the mass, and then you've multiplied the speed by 8, so that's times 64. So it'd be times 128 times bigger, numerically. So there's 3 marks. So I guess there's like 1 mark for pointing out what their speeds are. There's 1 mark for relating that to kinetic energy, I guess, and there's 1 mark saying, so yeah, because it goes up as a factor of 8 squared, it'll be times 64 from speed, and then it's times 2 from the mass. So that's the difference. Sure. Makes sense to me. 4.5. Oh god. There we go. Yeah, that made that 4 looks much better now. 4. We got another choice. The kinetic energy of the hailstones measured in joules. Which of the following is the same as 1 joule? We've got Newton meters, newtons per meter squared, and Newton meters squared. It is 1 Newton meter. And that you can actually tell. So if we look through our little equation sheet, there should be one to do with energy somewhere. There we go. Work done is force times distance, and work is so work done is measured in joules, force is measured in newtons, and distance is measured in meters. So that's a way you can check. You've got newtons times meters there, and that equals joules. As long as you remember that work is the same as energy, then you can say that yes, joule is 1 Newton meter. So that's nice and easy. 4.6. Figure 8 is repeated below. Thank you. I loved figure 8. I love it the second time around. The hailstone hit the ground at a terminal velocity of 25 meters per second. The hailstone took 0.06 seconds to stop moving. Okay. Sure. That's a strange way of saying, hit the ground after hitting. I don't know. Determine the average force on the hailstone as it hit the ground. Oh, right. As in when it started touching the ground and when it finished disintegrating into the ground. The average force on the hailstone as it hit the ground. Use information from figure 8. Right. So we want to find its mass first. That'll be important. So from 25, it comes down to around there. So that's about 18.5 grams. So we'll say 18.5 grams for its mass. And we want the average force on the hailstones that hit the ground. Okay. So, yes. What have we got? We've got time is 0.06 0 seconds. I guess we'll keep that 0 in, why not? And its velocity was 25 meters per second. Sure. And we want the average force on the hailstones that hit the ground. So we can work out its kinetic energy. We can turn that into a power because we've got the time. Yes. The average force. Well, I mean, we also have energy. And the average force. Right. Let's have a look. Have a look at our thing. Right. Force is change in momentum divided by time taken. This is what we want. Have a look. Okay. Well, best of luck, phone. Do your best. It's a shame your owner hates you. So the change in momentum, our delta V, really extreme. Oh, good. Well, I'm glad you enjoyed it. This is something different Sundays, and I have a physics degree. Why not use it once in a while? Yeah, I figured this was a relatable way to get to people doing physics that most people should at least have some kind of grasp with. Enjoy the rest of your night, and you, Chosky. Take it easy. So our delta V, it's going from 25. I love using my. Fair enough. You do what you do, you know. 25 minus 0 is 25, so that's our change in momentum, our change in velocity rather. So the force is mass times this delta V divided by the time taken. Okay, I guess we'll put that as delta T then, because that is our time taken. And that is, so the mass is 18.5 grams, which is 0.0185 kilograms. 1, 2, 3, yep. So 0.0185 times by 25, and all of that divided by 0.060. Sure. So that force is equal to 0.0185 times 25 equals that, divided by 0.06, which is that. Okay. The average force is hit the ground. I mean, yeah, fair enough. So that is 7.708 newtons. I mean, normally you do it to 3 significant figures, so we'll do it to 3 significant figures, and we do 3SF. So 3 significant figures just means the first 3 digits that aren't 0. That's what you round it to. I figure that's reasonable. Newtons, 7.71. 7 newtons for a hailstone. It's very fast though, so that makes sense. We're on to number 5. 5.1. Figure 9 shows a balance used to measure the mass of 5 tomatoes. What is meant by centre of mass? Oh, well, okay. I mean, the centre of mass is... the COM, centre of mass, is the point inside an object where you can consider all of the mass exists. All of the mass exerts its force, where all force done on it, or where all the mass resides. Sure. It's like the balancing point, right? So you know that when you've got that ruler and there's that trick where if you bring your hands close together, you'll find the center of mass. That's the center of mass that you're finding, right? So that's essentially that. Cool. 5.2. Calculate the mean weight of a tomato. Okay, well, that isn't just for show then. We've got 3 dashes and then the next one, so each dash must be 100 divided by 4, which is 25. So that mass of 5 tomatoes is 425. So we can say mass of 5 equals 425 grams. So that means the mean mass, that was such a small a, look at that, equals 425 grams divided by 5. That went so wrong. And that's a G, not a... I'm going to get rid of that G. 425 divided by 5. Which is 85 grams. There we go. That's the mean... Oh, we want the mean weight. Mean weight. Weight is not mass. So when we say weight here, we're not talking about kilos, we're not talking about pounds, right? We're talking about newtons. So the weight is the mass times by G, the gravitational field strength. So that is 85 times 9.8. This is why you read the question. It is very easy to do something like that, right? 833 newtons. There we go. That's the mean weight. Yes, I know that means nothing to me, but it wants a weight in newtons, and that's what you need to write down. So make sure you do. If it wants a weight, you give it a weight, not a mass. They are different things. Balance in figure 9 contains a spring that compresses when the tomato is placed on a balance. In figure 10 shows the spring with no force and with 6 newtons force. Sure, fair enough. Determine the spring constant of the spring. Ooh, spring constants. That's something I've not really done. We've got energy here equals a half k e squared, where k is our spring constant. So that's what we're interested in. In fact, is there something that relies on force? Just checking these higher ones instead. No, nothing else. No other equations we can check. Yes. There we go. I figured there was something I'd missed. Here we have force equals the spring constant times the extension. Because we know the force acting on the spring when it's got 6 newtons. And this extension here, so our extension is 1.5 centimeters, because extension and compression are the same thing, just the other way around. So that is 0.015 meters. Yep, good, just checking out my head. We know the force, so let's put the numbers in. We've got 6 equals k times 0.015. So k is 6 divided by 0.015. And that is some large number, which I can't do in my head. So that is 400. So it's 400 newtons per meter. And that's why we convert it from centimeters to meters, to make sure that the units are correct at the end as well. Good. Okay, 5.4. So there you go, that was one time I actually did have to use the physics equation sheet, because I have not used extension of springs in a long time. Explain one property of the spring that makes it suitable for use in the balance. That's an interesting question. A property of the spring that makes it suitable for use in the balance. Well, okay. In the balance. So, yeah, because we've got the mass. So we've got the... So I suppose this is about direct proportionality, I'd guess. So mass of objects are directly proportional, to its weight. That sentence doesn't really make sense, but I think you get what I mean. Very proportional to weight, and as we just showed and because F equals KE, the extension of the spring is also directly proportional to the object's mass of objects directly proportional to weight. The object's weight, and therefore the object's mass. So essentially what I mean is, basically, for any given extension of the spring, you can calculate the mass of the object on the balance very simply. That is what I'm trying to say. Is that, yeah, you're going to have a distinct extension for every different kind of force, right? That's why it's suitable. So the property of the spring is that the extension is proportional to the mass of whatever's compressing it. That's my point. Galaxies contain billions of stars. I mean, that's big if true. I don't believe it, frankly. Compare the formation and life cycles of stars with a similar mass to the Sun to stars with a much greater mass than the Sun. That's crazy. I don't think I knew really about the life cycle of stars until first year of university. I don't remember doing anything like that even at 18 in school. And you guys are doing it at 16 now. That's interesting. Okay. Alright. 6 marks. This is a big question. Jeez. Okay. So want some decent detail. Right. Well, what is the universe made of? Does everyone know? It's mostly hydrogen. And then it's about 3/4 hydrogen, about 1/4 helium. This is the known mass, I should say. This is not including dark energy, dark matter, all the rest of it. In terms of observable mass, is about 75% hydrogen, about 24% helium, and then everything else. So, oh god, I guess I'll do this in like bullet point form. So we start off with a nebula or cloud of gas. Cloud of gas, mostly hydrogen and helium. 75%, 25%. Mostly hydrogen and helium. That about there. Gravity pulls the gas together into a protostar. I will be amazed if they're actually using the term protostar. So all this gas comes together into a protostar. So this comparing, so this for both, this is so all stars. Hey now. All stars. Do that. Fusion begins in the heart of the star. Fusion begins in the heart of the star, exerting pressure on the outer layer, the outer shell. Gravity. So what's it do? There's a balance. So eventually, balance of force between the fusion. Balance of force between the fusion pushing out, and gravity pulling in. And then that's how you get a stable star. Okay. Okay, and then for similar, so approximately sun mass. Star burns out and expands into, oh, I suppose I should say, fusion begins at the heart of star, creates elements in periodic table, creates elements going up in the periodic table, by proton number. So up to iron. Doesn't go past iron. That's where there's a graph which looks something like that. And oh wait, no, it looks more like that, and then it's just downhill from there. And that, so basically this is how much energy you get, and then this is the proton number. So as you fuse elements together, you get more energy than you do putting them in until you hit iron, which is around here, and then fusing past iron, you don't get energy back, and so that's why stars, while they're burning, don't produce anything greater than iron. So going back to our question, we're going into way too much detail, but this is 6 marks. I gotta be serious about this. Going up in periodic table by proton number. Proton number up to iron. Didn't I just write this? Up to iron. I must have gotten rid of it by accident. Balance force between the fusion pressure and guide product. Star burns out, so iron core forms in the star. Yeah, and then near end of life, star's core is completely iron. So for a sun mass star, the outer shell expands and star becomes a red giant. Sadly, we know now that our sun won't supernova, which would be very beautiful, but, well, not like we'd ever see it anyway. Red giant compresses into a white, or blows off, I think. Outer shell of red giant blows off, leaving a white dwarf. Eventually, white dwarf becomes black dwarf, and then that's kind of the end of the lifestyle. Higher mass, much higher mass stars. We've got, I don't like how I decided to stop doing capitals there. Much higher mass stars, I suppose they still become a red giant, so there's that. But then star supernovas, releasing higher proton number elements into space. Leaves either a neutron star or black hole, depending on mass. Okay, so we've got some points talking about all stars. We've got how stars around our sun's mass goes, and then much higher mass. That's basically the only difference, though, is how they die. Ours will just turn into a black dwarf slowly, not a red dwarf. Shame, but that seems about right. God, look at that Milky Way! Woo, radical, bro. 6.2. The points on figure 11 represent galaxies that are moving away from the Milky Way. Sure. Each arrow represents the velocity of the galaxy relative to the Milky Way. Yes, because the Milky Way isn't stationary. We are moving. Light from all galaxies represented in figure 11 is redshifted. Describe what is meant by redshift. Okay. So, let's see. So as light is emitted from objects moving away, I mean, this is just Doppler shift, but with light, right? As light is emitted from objects moving away, the frequency is shifted towards the red end of the electromagnetic spectrum, i.e., frequency decreases. What? No, it doesn't. It increases. The wavelength increases, frequency decreases. No. God. Yes. Man, wavelength increases. Yes. I.e. frequency decreases. Yes. Yes, because gamma rays look like that, radio waves look like that. So yes, the frequency decreases. So, and that's what redshift is. It shifted towards the red end. So objects moving away from us, I guess I should say, from us. As light is emitted from objects, the frequency is shifted towards the red end of the arrow. Yeah, frequency decreases as it moves away. That's basically it. Kind of confused why that's 2 marks, but I suppose I'll find out when I look at the marker scheme. 6.3. Explain how figure 11 provides evidence for the Big Bang Theory. Well, this is it. So, what we have is the galaxies further away are moving away from the Milky Way faster. So this implies that on average, all galaxies are moving apart from each other. So yeah, every galaxy is moving away from each other. So going back in time, this implies that at some point all of the galaxies were much closer together, the inevitable end being that all mass existed at a single point. So, and that is the Big Bang, right? That all mass came from one single point and exploded, and so we get everything we see today. Cool. 6.4. Sometimes scientists have to change theories about the universe. Why? Why do we change theories? Observation is why we change theories. So scientists make an observation that doesn't agree with their theory, essentially. I mean, that is the reason Give the reason why. It's not a reason, it is the reason. You don't fit your observations to your theory. You make a theory, and then if it fits the observations, it works. Until one day you make an observation and the theory you were working on doesn't work anymore. And then you have to do something else. You have to make a new theory. Which is why supersymmetry is very iffy. But that's not for here. The national grid uses transformers to change potential difference, voltage. I don't like that they always say potential difference. It's just voltage, man. Figure 12 shows transformer. Yeah, we've got the input, A, B, we've got a few turns there, load of turns there, and that. Right. Identify the parts of transformer. Fine. So A, well, I mean, it's a coil. But then C is also, B rather, is also a coil. I think it needs a bit more. And then C is the iron core. I'm pretty sure in our thing they say what they're called. Primary core and then secondary core. Yeah, so here we are. We've got, because there are equations to do with these kind of transformers. So A is going to be our primary core then, because this is where our input, and then B is our secondary coil. So that's the primary coil, and this is our secondary coil. And then C is our iron core. Very nice. 7.2. There's an alternating input voltage of 230 volts. Determine the output voltage. And you can use the equation sheet. So the equation sheet is just, I see here the voltage across the primary divided by the voltage across the secondary is the number of turns, right? And it's the same way around. So essentially, if we know that it's 230 there, it's going to be 6 times as much over there. So I actually have to I still have to write this out though. So, God, I don't want to write all those words though. I don't know. V1 over V2 equals A over B, where A is our primary coil and B is our secondary coil, as I said that. So that is equal to 230 over V2 equals I'm getting a bit close to the camera there, but that is equal to 200 over 1200. That's our A and B. It's 200 and 1200. So rearranging that, you get V2 equals 230 times 1200 over 200, which, as I said earlier, is just 6 times that, which is 1380 volts. But we'll just double check that. 230 times 6, 1380. There we go. I didn't get too close. Excellent. Didn't go behind my camera. And that's our output potential difference. Yes. 7.3. The input voltage causes an alternating current. Explain why there's an alternating current in the output when a transformer is connected to a circuit. Because you've got an alternating current. Right. So you need to say how the current goes across as well. So, I mean, it's exactly the same reason, right? So, why have they? Because I suppose it's power arguments is why the power of the start is power at the end. So that's why it's done VI rather than V over V equals I over I, even though it's the same thing. But whatever. So what am I actually going to say? It's kind of hard to come up with an actual argument here. Explain why there's an alternating current. Well, it's because when the transformer is connected to a circuit. Well, because it's just what you said, you've got an alternating current. So similar to in right, okay, there we go. Similar to in 7.2, the current in the secondary coil is related to the current in the primary coil, depending on the number of turns for each coil. Therefore, if there is an alternating current in the primary coil, there will be an alternating current 6 times less in the secondary coil. 6 times lower. Because the so the voltage increases, but the current decreases, I believe. Yeah. Well, yes, because we've got yeah. So the voltage, because that voltage in the secondary is 120, it's 6 times greater than that. So the current must be 6 times less for that equation to work out. So yes. And it was in paper 1 as well, about how the current changes as well. Good. Yeah. Makes sense. 7.4. Figure 13 shows a large cable supported by 2 wooden poles. The cable is connected to an electricity supply. We've got a current of 50 amps. We've got the Earth's magnetic field. Wow. There's a force on the cable due to the Earth's magnetic field when the current is in the direction A to B. What is the direction of this force? Down, left, right, or up? Okay. So, this is... Oh, God. It's one of those... Well, so it's one of the hand rules. It's the... I remember someone saying that it's really fun to invigilate, as in to look after the students when they're doing a physics exam, because there's at some point where all the students start throwing up gang signs in electrics papers, especially because we have like left hand rules and right hand rules, and there's bit where you're doing that to make sure things are going the right way. So I believe this is Fleming's left hand rule, where you have your second finger, which for me I cut the other day. This is second is your current. Your first one is the field. So we've got our magnet. So we've got our current going forwards. We've got our field going right, and then your thumb, the M, is motion. So that means that it gets a force down. I'm pretty sure it's left. It could be right. And obviously, if it's the right hand, and I do all that, it'll point up. So it's either down or up. I'm pretty sure about that. I think it's down. I think it's Fleming's left hand rule. But we'll see. Find out in a bit, because there's only a couple of questions left. I've only got 45 minutes. I've got to... I'll be fine. The cable experiences a force of 0.045 newtons. Magnetic flux density is that, and the current is that. Calculate the length of the cable. Wow, okay. That's one of these. Force on a conductor at right angles by carrying current equals that. Okay, F equals BIL. Yeah. That's God, right. BIL. Oh my god, that looks horrendous. There we go. BIL. Yay. Okay. Right. Before we put numbers in, 60 micro Tesla equals 0.12346. 1, 2, 3, 4, 5, 6. Yes. That many Tesla. So get rid of the micro. We need to make everything normal units. So the force is 0.045. The magnetic field B is that times by our current, which is 50. And that is times by the length, which is what we want to find. So L equals 0.045 divided by 50 times 0.1234, right? So it's that. Whatever that is. 0.123. Oh no. Do it the right way around. 0.045 divided by, we'll open a bracket, 50 times 0.12346, close the bracket, and equals 15 meters. That's a nice, clean answer, which I'm very happy with. State an assumption you made. Ooh, an assumption. Well, in the equation itself, it says at right angles to magnetic field. So I guess we're assuming the whole cable is straight, as in it doesn't sag. I think that's a decent, yeah. The cable is completely straight and doesn't sag. Yeah, i.e. the cable looks, so if I've got my pole here and I've got my pole there, the cable looks like that. It doesn't look like that, right? That's what I mean, but it doesn't sag, it is perfectly straight, which obviously isn't true. So yeah, it won't be, that won't be the true answer, but that's the answer they're looking for, I'm pretty sure. Question 8, final question, and we've got 40 minutes to solve it. Sure, diving bricks sink to the bottom of a swimming pool. Fair enough. Figure 14 shows a diving brick. So it's 10 by 10 by 25 centimeters. Swimmers practice diving to the bottom of the swimming pool to pick up the diving brick. Explain why the force on the brick at the bottom of the pool caused the brick to be stationary. Okay, so we draw our brick here. Get it nice and brick-like. What are the forces? So this is why we need free body diagrams. So we've got our weight here, which is mg. And then force up, we've got the normal reaction force. And because it's in a pool, there is also a buoyancy force. So I guess I'll just call that FB for buoyancy. If I had emojis, I'd put the red B there. It would make me laugh anyway. Explain why the forces on the brick at the bottom will cause the brick to be stationary. So in this case, W equals N plus FB. So that means velocity is 0. So because A is 0, so that means the acceleration is 0, and it's a brick, it's on the ground, its velocity is 0 as well. So that's kind of my answer. I guess in words, I mean, I'd just say that in words, right? I'd just say the weight is equal to the normal force plus the magnitudes, that is. Technically, I'm talking about the magnitudes here. It's equal and opposite to the reaction force and the buoyancy force. So that's why it's stationary, basically. 8.2. When the brick is at the bottom of the pool, the top surface is 2.5 meters below the surface of the water. Okay. I'll just mark there. 2.5 meters. The force acting on the top surface of the brick due to the weight of the water is 637 newtons. Okay. Sure. Fair enough. Gravitation field, something like that. Calculate the density of the water. Okay. So the density is mass divided by volume. So what do we know? Well, what equations do we have? Let's check that. We want to look at pressure. So we've got, there's a pressure argument we could make, which makes sense, I suppose. We know that pressure is the force divided by the area. So, okay. Sure. So we've got we want to find rho. Our pressure is force over the area. And we know that that is 637 newtons. And we can work out the area, because that is it's the top surface of the brick. So that is 10 times 25, which is 250. And that is equal to, where is it? This pressure due to a column liquid equals the height of the column times the density of the liquid times the gravitational field strength. And we know the height is 2.5 meters. And we know that G is 9.8. So we can rearrange that to say that rho is 637 divided by 250 times 2.5 times 9.8. And I'm really hoping that's about 1. Oh wait, I'm an idiot. What have I done? That's in centimetres squared. Aha! I don't want that. I want that in meters squared, which is 0.025. Right. 0.025. Think of it as 0.1 times 0.25. If you just want to convert them back into centimeters, from centimeters into meters, and that is 0.025 meters squared, right? Check units, very important. Right. So we've got all that. Let's do some calculating. 637 divided by brackets 0.025 times 2.5 meters times 9.8. Like that. That equals 1,040 kilograms per meter cubed. Very nice. So yes, the density of water, incidentally, it's very good to know the density of water, say H2O, is, so yes, you can say 1,000 kilograms per meter cubed. But what does that mean, right? That is the same as 1 gram per centimeter cubed. What does that mean? All right, that's also 1 kilogram per liter. Right, so if you have a 2-liter bottle of Coke, oh god, that's very it's incredibly dodgy. Yeah, there we go. There's our horrible 2-liter bottle of Coke, right? Coke. Right, I'm losing my mind. Right, so that's 2 liters. And so that means it is also 2 kilograms. So that's just a nice frame of reference. So if you ever hear liters and you're talking about water or anything that's the same kind of density, it's 1 kilo. Anyway, I'm going to clear that board. What are we doing here? So we've done 8.2, right? That was the one we just did. Excellent. Right, 8.3 then. It's just a small aside. 33 minutes, right. Professional divers trained in a very deep swimming pool. Density of the water is not the same as density of water in 8.2. Of course it isn't. The diving brick was dropped in the very deep swimming pool, but it's the same brick. When the brick was at depth of 2.5 meters, the force was 618. Okay, so we can just work it out the same way. Figure 15 shows the diving brick at the bottom of the very deep swimming pool. Determine the force due to the weight of the water on the top surface of the brick in figure 15. Okay, and this is the last question. Wow, alright, fair enough. So, what can we do? Is there an easier way? So what we can do is we can work out the density of this water and then plug everything in. And that's kind of the simple way. But also, I think there's a simpler way. But Because you know this distance and you know the earlier distance, I think you can just multiply that. But let's be explicit, actually. So let's find out the density. So we'll do it exactly the same way we just did. It's just in this case, our density is, instead of 637, it's 618. And it's divided by, it's the same area, the same depth, 2.5 meters, and G is still the same as well. So all those other numbers are all the same. Times 2.5 times 9.8. So what we can actually do is just divide that by 637 and then multiply it by 618. That would also do it. So divide that by 637 and multiply by 618. And it is 1008.979 ... right? Kilograms per meter cubed. But that's not the answer. That's not the question. We want to determine the force due to the weight of the water. And that is pressure due to, so we've got we want to know the force. So that is the area times by the height column times by the rho, and then times by G. So we just found out what rho is, and we know all these other things already. So it's 0.025 times, make sure we get the height right, is 49.9. It is not 50. Times by 9.8, and then times by 1008.979 ... right? Good thing about calculators is they can remember numbers. So I'm leaving out in there, and then times that by 0.025, 0.025, then by 49.9, and then by 9.8, and we get that, and we want that in 3 significant figures, don't we? That's very high pressure, but don't see anything we've done wrong, so it's just very high. Give your answer to 3 significant figures, so we'll just say 1, 2, 3, 0, 0 newtons. 12,300 newtons. Which is very high, but, well, that's the thing. I think it's only... and that's the end of the paper, so call that time. So, because what was it? I think it's like... If you imagine all the pressure of the entire atmosphere on you right now, it only takes... To get that equivalent amount in water, you only need to go down like 6 meters, I think, in water, in the sea, for it to be the same as a whole atmosphere of pressure on you. Water is a lot denser than air, so that's your fact of the day. Water is denser than air. Marking time. Here we go. So the first 2 questions we already did in the foundation paper. They were exactly the same. Question 3, however, was different. So we've got wet, icy road conditions. Nice. And negative gradient in the road. Downhill. Yes. Going downhill. Allow going downhill. Cool. 3.2. Distance is speed or time. Yes. Yeah, so increases for extra time increases. Yes, distance is speed times time. I suppose I basically said that. Because I did say the car was moving, so that indicates speed. Right, 3.3, we ticked mean reaction time increases and change is not the same. Mean reaction time, change is not the same. Excellent. 3.4. So this is just how long does it take to go across? 75 seconds. Yep, we got the 1500 of 20. 1500 is that, and distance is 1,500 meters. That's why you do those conversions. It is worth a mark. 3.5. Velocity is a vector, speed is a scalar. Good. Road is not straight. Road curves. Yes. Therefore, direction changes, so velocity increases. Yes. Excellent. Velocity changes, rather. 4.1, net force. Yes. Yeah, weight is greater than it is. Yeah. Allow initially weight to grow. Yeah, there's net force. As the velocity of the hailstone increases, air resistance increases. Depends on the speed of the hailstone. As the air resistance increases, got it right there. Until air resistance becomes equal to the weight of hailstone, when magnitude of air resistance equals weight, there is no longer a net force. Resultant force. So no net force means no. So yeah, the resultant force is 0. Put both in that mark really. As mass increases, the weight increases. Let's go 4.3. Check that was the one we said. Yes, it is. It's good. 4.4. Okay, I just wrote it all in numbers, but yeah, I don't think I could be bothered to actually write it. Kinetic energy depends on mass and velocity. Yeah, I mean, I wrote that, so that actually is a mark. As mass increases, so does velocity. A statement is required. Okay, well, kinetic energy was, yeah, I mean, can be scored by relevant calculations. I said all that, so yes, times 128. That works. 4.5. 1 Newton meter. Yes, that's the one we said. 4.6. 7.71. Okay, it says allow 7.7, and it puts 7.708 7.71. So that's allowed. That is what we wrote there, and then the mass is 0.0185. Yes, very good. Cool. Allow 0.018 to 0.019 inclusive. Board 5. The point inside an object where you can consider all the mass resides, from which weight may be considered act, where mass appears to be concentrated. Mass is concentrated. Yeah. Sure. Okay. The point from which weight may be considered an act. Fine. Why not call it a center of weight then? Anyway. Mass of 5 tomatoes is 0.425. Yep. Mean mass is 85. Guys, I screwed up. I wrote it all in grams. No! All my talk of units. And I screwed up because I was too tired. It's 10 o'clock, man. I'm tired. No. Oh, I thought we were getting 100% on this one. But no. It's not to be. Fine. I screwed up. I left it in grams. I even wrote grams. I just didn't change it. Awful. Awful, awful, awful. I should get rid of my degree. It was useless. 6 is that. That's 6, and that's 400. Good. 5.4. Deforms elastically, so will return to original shape, or compression is directly proportional to force applied, gives a linear scale. Yeah, that's basically what I said. All stars form in a cloud of gas and dust. Nebula, yep, cloud of gas, mostly hydrogen. Yeah, I mean, that's all there. Forms a protostar. Ah, fuck off. People say protostar at 16 years old. Fusion begins. Small nuclei into larger, you're going up in periodic table. God, we're getting every point here. Main secrets are, yep, gravity, balance force between fusion and gravity. We got every point there. And we added one. Stars about to expand to become a red giant. A red supergiant. Right. Well, because a red giant. But, okay. These are the comparisons, I guess. Stars about the same size contract to become a white dwarf. And, yeah, the bigger ones explode. Yeah. Cool to become black dwarf. And that's a neutron star or black hole. Cool. Yeah, we definitely got all the marks there. 6.2. The observed increase of wavelength. Well, I said decreased frequency, but that's the same. As galaxies move away. Yeah, cool. Yeah, increase in wavelength is the same as decrease in frequency. That's the exact same thing. The furthest away galaxies are moving away the fastest. Galaxies further away are moving faster. Yep. Which suggests at some point all of them start at the same point. Yeah. Yeah, or everything, all the masses at a single point. Make an observation doesn't agree with theory. There are new observations, evidence does not fit the current theory. Yeah. I mean, that's that. Or you can specifically say dark matter, dark energy. That's quite funny. Primary core, secondary core, iron core. Yep. Yeah. 230 over voltage equals 200 over 1200. Yep. And then it's that, and then it's 1380. Wonderful. 7.3. The alternating current causes. Oh, it wants you to talk about magnetism. Oh, that's why. Ah, right. Okay. Oh, right. I completely. I brought that up. Yeah, magnetism. That's why it really wanted the reason why. I couldn't tell what it was going for, but that's change magnetic field. Yeah, I didn't say that, so I don't get those marks. 7.4, I believe I did say down. Yep, top one was down. I said the top one, and that one's down. 7.5. Okay, so yeah, B is that. Then we said that, and then we said that, and then we said 50 meters. The wire force at right angles to magnetic field. The cable is straight. Yeah, cool. Could also have current constant, fields uniform, plenty of other ones you could have. Quite a few assumptions made, really. Upthrust. Upthrust. I've never heard the term upthrust before. Not in buoyancy. Well, I've got normal contact force, got the weight, and yeah. Buoyancy. It's buoyancy. It's upthrust. What is upthrust? Okay. Oh, right. Okay, we've got a couple of methods here. So, work out the area. What did we use then? So we didn't work out the pressure. Yeah. We just did it on... Well, I mean, we got the right answer. So, it can't be that bad. The volume of the water. We didn't get the volume of the water column. I mean, we showed our working, so I mean, I'm fine with that. And then this one was 12,300, and again we showed working again. So yeah, there's all the numbers there, right? So I'm going to go with that. Allow maximum of 2 marks if 50 meters used. Don't round it just because you think it's better. So it's a sad day for science. We lost 3 marks there, and we lost another mark there. So that is 96%. That was our worst paper today. There we go, and we're done marking. Oh! So what have we learned today? Oh! We've learned that just because you have a degree doesn't mean you're necessarily going to get 100% in papers for students, for those 16-year-olds, without revising. I must say, if I had the one thing, if I did have to revise for some reason one of these papers, I would be looking up the things that you just have to know, the things you just have to remember. Things like here, that you have to talk about the magnetic field, something like that, because I just got confused. But of course it's talking about magnetic field, and you need to talk about it. But I haven't thought about transformers in 10 years. Like, I don't care about transformers. I don't use them. I mean, I use them sometimes, I guess, but I mean, not. I don't need to explain how they work all the time. So, yes, it's some things, and just being more explicit, I suppose. So in our first foundation paper, we lost 3%. God, look how big I was writing at the start. So all that was fine. What did I lose the marks on here? Yeah, so again, Transformers actually got me again. What was the other thing? Yeah, so the whole stuff about energy, like, yeah, renewable, non-renewable, that kind of stuff. That's all that sort of stuff. So thermal conductivity, yeah, there's just a lot of areas of physics that I've not bothered with looking at for a while. And that, I mean, that was just stupid. Just checking your equations, man. What was that about? So, yes, kinetic energy was the point there. 98%. So there we go. We've got a total mark 97 and 98 for foundation, and we've got 97 and 96 for the higher tier. So not too bad. Better than my actual GCSEs. I got 94 and 91%, but those I did the international GCSEs, which is a lot worse. The paper's like 3 hours long. These are just now 45. I wish my oh wait, no, that's maths. What did I do for physics? Oh no, maybe I did do AQA for physics actually. I don't know why I was thinking about maths. How did I do my physics? I don't remember the percentage I got on my physics one actually. It wasn't 2 papers, so the format's changed so much anyway since I was last there. So, anyway, it is 10:30. I've been talking incessantly for 6.5 hours total today. So if you've just caught the last of my stream, go watch the earlier ones, watch the whole 6.5 hours, and go along, see how much you can tell. To put it on the background, listen to me with some lo-fi vibes. But other than that, I'm going to call it there for the night. So thank you for joining. I hope you enjoyed yourself.